right. Welcome. Hello. Hi. Let's settle down. We're getting started. Okay. For how many of you is it your first time at the Flatiron Institute? Raise your hand. Okay. Nice. For how many of you is it the first time in New York City? Wow. Okay. That's impressive. Okay. Welcome. It's not like I can give you a fair welcome because I've been here 6 months, but there are others in the room who've been here much longer. So I'm sure they will give you advice on the fun stuff to do in New York City. Of course, this is going to be a fun school, but there's also fun outside of that. All right, welcome to the start of the summer school on the landscape of astronomical transients. It's going to be an exciting 2 weeks ahead. And to get started, I wanted to sort of just tell you a bit about the logistics, how the sessions would be like, and who to go to if you have questions. So just to introduce myself, I'm Kishalay. I am an associate research scientist at CCA and jointly an assistant professor at Columbia. My co-organizers for the school are Matteo Cantiello, who will be soon here later in the week, and Brian, who's here, who will be your first lecturer. Um, and I don't see Kristen here, but you've probably all been in touch with Kristen about all the logistical stuff. So Kristen is really doing all the difficult stuff for the school. So kudos to Kristen. I think she'll be here sometime, but anyway. Okay. Oh, I'll introduce Kristen a bit later. Okay, good. So why are we here? So hopefully all of you have seen this image already. Yeah, it's on the first look images from the Rubin Observatory. And does anybody remember what this shows? What is this? What special region of the sky is this? Anybody? Cluster? Maybe cluster? What cluster? Okay. I thought we selected mostly observers, but here we go. Okay. Yeah. Yes. So, yes. It's a Virgo. Yes. So yes. So yeah. Here we go, Kristen. So all of the hard stuff is being done by Kristen. So if you have questions, yes. Thank you. Okay, good. Right. So we're going to be spending 2 weeks thinking about what this new telescope and this new observatory and the new survey that comes with it is going to teach us about the universe. Brainstorm questions on how do we use this data stream to push directions that this data stream is well suited to push at. There are some things that this survey is going to be really good at, some things not so much. And we'll talk a bit about what the pros and cons are and how do we redirect our efforts to really maximize on the scientific potential of this huge survey that's coming online. All right, so just as a welcome, so unfortunately, our director, Julianne, was unable to join us today. She was going to, but then she had something. She was actually in Germany right now, so she couldn't make it. So on behalf of Julianne, welcome to the CCA. The CCA is positioned to address really difficult problems in computational astrophysics, all the way from theoretical problems, simulations, and to even data. So in case you are wondering, why are we having this school at CCA in the first place? The Rubin Observatory is going to be one of the biggest data challenges in not just astronomy, all of science, which is why I bolded science over there. It's really the amount of data that's coming is really requires careful thinking about what do we do with this. And collecting data is one thing, making scientific progress is a completely different thing, and those two don't necessarily go hand in hand always. And we'll try to think about that. How do we make progress with this data set? Okay, so you've probably seen all of this already from the sign up form, but we do have a code of conduct, just in a nutshell, please be respectful to others, respect, all of our different backgrounds that we all come from. It's really amazing that we were able to get a group of students that have both observers and theorists. And the hope is really to be able to encourage interactions between these two groups, which should always be talking to each other. And so please be respectful of your backgrounds. There'll be lots of parts of the school which you might be very familiar with. So, and there might be others who are not. So please help each other learn. If you don't know something, you can, please feel free to ask the instructors, your peers. The goal of the school is to really learn, regardless of what background you come from. So the general structure of the school, as you've probably already seen from the schedule, we're going to have two morning lectures. First one starting at 9, the second one starting at 11. Um, we'll have a coffee break in the middle at 10:30, and then we'll have an afternoon sessions every day, which will be almost entirely Python notebooks. So please go back to the email that I sent last week. These notebooks are being updated on GitHub. There'll be some notebooks that require some specific data download ahead of time. So please make sure you download them. In the room, we have Wi-Fi. So the Wi-Fi details are this code over here. So that's not the one that works with the uh, so you should be able to access the Wi-Fi, but it's still advised to download the bigger data sets ahead of time, just so that we're not all downloading big data files on the same Wi-Fi network at the same time. All right. So yes. So just before I proceed, was everybody able to access the GitHub, the notebooks that sent? Okay, good. Okay, because I think the first one today will be needing one large data file that should have been on Dropbox, and hopefully all of you had a chance to download. Okay, good. So again, we have a mix of people from different backgrounds, observers, theorists. So please help each other learn yourself, and of course, help the instructors learn as well. You might come up with ideas that we haven't thought of yet. So most importantly, have fun. So all right. So just a few logistical things before I hand it over to Brian. Um, so I'm told that there is a fire drill today at 10, but apparently because none of us or most of us here don't work at the CCA, we don't have to participate in it. So keep calm. Maybe Brian has to leave at 10. I don't know. Yeah, yes. So yeah, so there'll be a fire drill at 10. So, but just stay put. It's all good. The other request is that all of these sessions are being recorded. So for the speakers, please use the microphone. Also, when you're asking questions, please feel free to interrupt and use the microphone in front of you. So all of you have a microphone in front of you, and there is a button at the bottom which if you press it, that switches on the microphone. So that way we can also record all the interactions that are happening during the school. All of this is being recorded on Zoom. Right. So between the morning lectures and the afternoon sessions, we'll have catered lunch, which will be right outside this door. So it can get a bit crowded because we're about 35 people over here. So there'll be lunch served right outside. But we advise you that you take your lunch and you go to the 11th floor, which is where we have our food, so that it doesn't get too crowded over here. So you're always welcome to stay in the class and eat, but I suspect after spending 3 hours in a class, you won't want to spend another 2 hours in a class. So you're welcome to go upstairs. It's really hot outside this week. There is an option to go on the 12th floor, but it might not like that. But the 11th floor is always air conditioned. You can feel free to go up there and eat, take your lunch and eat there. All right, so we have name badges for all of you. Hopefully, all of you had a chance to collect your name badges. I think we would recommend that you try to wear those name badges, because I think most of us might not know each other. So it's a good way to introduce yourself to your peers. And let's see. Yes, so between the two morning sessions, we'll have a short coffee break of half an hour. There is coffee right outside over here. There are coffee machines right outside, which you're welcome to use. There are also coffee machines on the 6th floor. So just so you know, so CCA is the 5th and 6th floor of this building. So please try to stick within 5th floor, 6th floor, and the 11th floor. The other floors are other departments, and we don't want to, bother them with this huge group of people. So it's so we would advise advise you to just use the coffee machines out here. If it's crowded, go to the 6th floor or go to the 11th floor where there are more coffee machines. So that will be a half an hour break between the two morning sessions. All right. Yes, so again, the school is, hopefully we can make it as interactive as possible for all of you. Please ask questions of instructors, ask your peers. If you're completely new to a subject, then great, which means that you're actually learning something. Yes, any questions before I hand it over to Brian? Right. So just to introduce our first speaker, our first lecture is by Brian Metzger. Brian got his undergrad degree at the University of Iowa, and he went on to do his PhD at Berkeley, and then a postdoc fellow at Princeton. And after that, he's been a professor at Columbia, and now jointly senior research scientist at the CCA. And he'll be talking to us about the basics of transient astrophysics and the physics that drives the light curves and so on.
All right, good morning, everybody. Pleasure to welcome you here to CCA and to New York City. This is your first time, welcome, especially. You come at a hot time of year. Subways are unbearable, but hope you enjoy the visit. So yeah, I was tasked with today discussing some of the very fundamental aspects of astrophysical transient light curves. And I see that we actually have many experts in the room. So for some of you, this will probably be very boring or basic, and I apologize for that. But I know we have a large number of people who maybe don't think about theory. And as we go towards this domain, it's true for any type of transient. I've shown some exotic ones here, things that we don't necessarily detect that frequently or haven't been seen yet. Actually, most of these we have seen potentially, but these are, what I'm mainly going to focus on are more bread and butter transients. But I wanted to put this up here as just sort of the diversity of astrophysical events, which can be understood within the same kind of framework that we can understand more basic transient events. But what I wanted to say was that, I know for any class of supernova, you can go out and download a bunch of people's theoretical models. But my goal today is to try to explain to you at a very basic level what sets basic properties of transients, their rise time, their peak time, their luminosities, so we can understand, why we're able to actually discover these events in large time domain surveys, and then you can go back and dig into the detailed models and really appreciate some of the trends you see in that type of modeling. So anyways, the outline for my presentation today, and I want to emphasize again, if there's something you want to stop and ask, this is a school, it's not just me talking to myself, so please interrupt me. But the outline is I want to just sort of very briefly give you an overview of the transient landscape. So for select explosions, some of the more commonly detected ones, I just want to go over what are the basic luminosity scales, durations of those transients, the ejective properties that you might expect in terms of velocities and masses, and this sort of duration luminosity landscape, which of course affects very much what we'll actually be able to see with a given survey. Then I want to go into some very basics of what sets light curves, peak timescales, and luminosity scales. And then I'll apply sort of these basic understandings to two different types of events. One I'll call a pure explosion. So this is where you blow up a star, for example. So you have an initial heating of the ejecta, but then nothing else is really heating it substantially for a period of time. And so it's basically radiating as a result of that residual heat that was injected from the explosion. So an example here are type 2 supernova during their plateau phase. But then we have other sources where they would not be bright unless there was something continuing to heat the ejecta from the explosion as it expands. And that heating source can vary depending on what type of event you're talking about. So if you're talking about radioactive heating, then that's what's powering, we think, type 1a supernova and most type 1bc supernova, also kilonova. But I'll go over these examples. I'll talk about where there's a potentiality you have a central engine in some of these events. So you form a compact object which is injecting energy. This might be behind some superluminous supernova. You have many cases where the ejecta runs into something and the shock wave that it produces on larger scales, not the initial explosion of the star, but the shock wave it produces as it runs into material can provide a source of heating. And then we have other events where potentially the recombination of hydrogen can power the light curves, for example, luminous red nova. So I want to go over sort of applying these basic scalings to these different examples, again, just at the order of magnitude twiddly level, And then at the end, I'll talk a little bit about a more slightly more sophisticated way that still involves the simplicities. So I'm just going to go through, Saurabh will talk about this a lot more detail. I'm just going to go through a bunch of different types of things. So one of the most commonly detected transients in the night sky are type 1a supernova. We know these are caused by the thermonuclear explosion of white dwarfs, but there's a number of questions. Exactly why did that white dwarf explode? Was it accreting from a companion star that was pushing it up against the Chandrasekhar mass and it got very dense in its core and that caused it to explode? Or was it in a binary with another white dwarf where the two stars merge, and after a very complicated dance that actually isn't always so abrupt as this, the remnant from that may themselves ignite and explode. And there are many open questions which I'm not going to address, but even though this is one of the most commonly detected transients, we have many open questions. Which of these channels dominates? Are there more exotic ways to get two white dwarfs together? Is there stuff around them when they explode? It seems like there's a lot of diversity of one. There's not just one type of class 1A. There's many variations of this, and so all of these may be true to some extent. But typically speaking, in terms of what we see, the durations, the luminosities of type 1a supernova reaching a peak of around 10 to the 43 ergs per second. They last typically weeks to months. When I say duration, I mean something, it's sort of a fuzzy notion, either not really the rise time or decay time. So how long is it near the peak luminosity? And since we're blowing up a white dwarf, typically the ejected mass is a solar mass, and you're 10 to the 51 ergs of kinetic energy. So you have about 10,000 kilometer per second expansion speeds of that material. And as you know, type 1As are standardizable. So depending how bright they are is correlated with how long they last. And so if you correct for this, you can standardize them and then use them, for example, for cosmology, at least the most luminous, not the most luminous, but at least the standard most common type of 1A. We have core collapse supernova. So this is when massive stars collapse at the end of their nuclear burning evolution. The core implodes, produces a proto-neutron star, which is very hot, radiating neutrinos, and some fraction of these neutrinos, possibly aided by rotation and strong magnetic fields, basically reverses the implosion and blows up the outer envelope of the star, potentially leaving a compact object. And we have different types of supernova from these core collapses. We have the one that involve explosions of hydrogen-rich stars, which produce type 2, or those which don't have hydrogen in the spectrum, type 1, B, or C, depending on whether we have evidence for helium in the spectrum. And the difference is, type 2s phenomenologically, you sometimes get these plateau phases powered by, well, they're not powered by, but mediated by the recombination of hydrogen. And the type 1 BCs tend to evolve a bit faster, but typically speaking, we have durations of, several weeks to months. Luminosities, which are a little bit lower typically than that of type 1As, maybe 10 to the 42 ergs per second is typical, although we have extreme examples of superluminous supernova, which are much brighter. And since we have massive stars exploding, and most of the time we form a small neutron star, most of the star is ejected. So we have typical ejected masses of order tens of solar masses. And since the energy is still 10 to the 51 ergs, typically the ejected speeds are somewhat lower than in the case of 1As. We have merging neutron stars. So if you take two neutron stars and put them in a tight binary, gravitational waves bring them together. They collide, and due to various processes that happen right before and after that collision, some of the neutron star material is ejected into space, either dynamically or through outflows from the accretion disk. This is a very energetic event, produces, we think, a jet from the newly formed black hole. There's different ejecta, but the point is you eject some neutron-rich material. It creates heavy elements which are radioactive, and they cause the ejecta to stay hot and result in a fast and dim transient that we refer to as typically as a kilonova. So typically kilonova peak on a time scale, depending on what band you're talking about, but typically a time scale of days. And they have luminosities of order 10 to the 41 or 42 ergs per second. So not that much dimmer at peak than a supernova, but substantially faster. And we have much less ejecta mass, so 100th of a solar mass, and expanding at a higher speed than in supernova. So we'll come back to that. That's the reason why they evolve so quickly. These are, of course, primary candidates for counterparts to LIGO sources. And of course, if you replace one of the neutron stars with a black hole, and assuming some of that neutron star gets tidally disrupted rather than swallowed whole by the black hole, then you can also get a kilonova in principle from black hole neutron star mergers. We have stellar mergers / common envelope events. So this is when you have two stars orbiting each other. One star is usually evolving off the main sequence, and it encounters the other star, begins to overflow its Roche lobe. If that process is unstable, meaning it doesn't just sit there as a nice contact binary, but the mass transfer onto the companion runs away, then you get this process where the other star can fall into or spiral into the envelope of the primary, and this results in a sudden ejection of material from that stellar envelope. And as that material expands into space, it powers something known as a luminous red nova. We'll come to these. These have only been discovered in fairly recent years. They have typical durations of months, typical luminosities which span a wide range, 37 to 41 ergs per second, let's say, depending on how much massive the star was and how much mass was ejected. So we have a wide range of ejected masses depending, some fraction of the companion envelope is ejected, and typically somewhat lower speeds than we get from supernova. So it's more related to sort of the orbital speed of the binary. And as Kishalay has discovered, we actually also have similar events that can happen when the companion is a planet falling into the companion star's envelope, and it produces an even dimmer and optically faster transient. Now, in the infrared, these things can last significantly longer, but I'm going to be mainly focusing today on the optical emission. And then finally, last but not least, of the things I'm going to talk about briefly, we have tidal disruption events. So this is when a star in a galactic nucleus gets put onto a very high eccentricity orbit that brings it very close to the central supermassive black hole. If the tides from the black hole overcome the self-gravity of the star is disrupted and forms these streams of debris, which fall back to the black hole over timescales typically of months. And assuming that debris is able to collide with itself or otherwise somehow, thermalize its motion, it's been shown in simulations that you produce this kind of enormous cloud around the newly formed black hole, which may also produce outflows of material. Whether they're bound or not is one of the open questions in this field. But these clouds are quite large, and they have large photosphere radii for a reason we're trying to understand. And so this can power a fairly luminous optical transient, which is typically lasting for months or so. Quite high luminosities comparable to the Eddington luminosity of the supermassive black hole. These are usually million or 10 million solar mass black holes, so quite high luminosities. And again, the stars we're typically disrupting are around the mass of the sun. They could be more or less, but sort of the material in this cloud is a fraction of that. So typically a solar mass or so. And the line widths indicate speeds of order 10,000 kilometers per second. Okay, and there's actually two phases to TDs. It's clear there's a phase where there's this big photosphere. We're debating why there is this big photosphere. And then at late times, it seems like you do actually form a compact accretion disk around the newly formed black hole. So anyways, that was just my brief kind of primer on these different transients. You can put them in this type of famous diagram popularized by Monty Kesselwald between where you have the peak absolute magnitude or equivalently peak luminosity of a transient versus its characteristic timescale. And you have very common things like classical nova, which are mostly seen in our own galaxy and nearby galaxies. You have common things like supernova, so ordinary thermonuclear supernova, and core collapse supernova, which I mentioned. And then you have things that have only been discovered in the last decades or so, like superluminous supernova, which are much brighter, tidal disruption events. And then we have these ilots, of which luminous red nova is that's just that. I don't want to go into what ilots are, but the luminous red nova are sort of down here in between the nova and the supernova. And then we have these very short duration things. And one thing to emphasize on here is just that part of the reason that we detected first thermonuclear 1As and core collapse is because they're both common volumetrically in the universe. They're bright and they last a long time. So our surveys can pick them up easily with a reasonable cadence. It gets much harder to detect things, obviously, that are dimmer or fast evolving, because they might evolve faster than our surveys taking data. And so that's why we haven't, for example, blindly detected a kilonova yet, or at least I don't think we have. But in some cases, things are just so freaking common, like nova, that even though they're dim, they can still be detected. Okay. All right, so now I'm going to go through just sort of the basics of generic transient, and you could sort of imagine all these things I talked about. What is the common thing? There's some mass being ejected into space with some velocity, some energy, and we would like to know what kind of light it produces. Okay, so we imagine that we have some generic ejecta mass m with some kinetic energy, which then defines an average radial velocity. I'm not talking about the velocity of the fastest part of the ejecta or the slowest, just some average, so I'll call this V ejecta. And in general, this ejecta will have some density profile. So the density will vary as a function of distance. And typically, if you're talking about the inner layers, not the outermost layers of the ejecta, this is a pretty flat profile. So just imagine like a constant, roughly constant density expanding sphere. And if you wait long enough after the explosion, there's this assumption of so-called homologous expansion, where the shells have reached this beautiful phase where each shell is expanding linearly in time given its velocity. So every velocity layer, fastest material out in the outer part, slowest material in the inner part, and they all meet at the origin at the time of the explosion. And so if you have this kind of homologous density profile, then you can define an average radius of your ejecta, which is the average velocity times the time since the explosion. Again, this is not the surface, not the center, it's where roughly most of the mass is. You can define sort of a volume associated with its average radius, a density associated with that average radius, which of course is decreasing. It was 1 over time cubed because the material is expanding linearly with time. And then you can assume that this ejecta has some thermal energy, okay? So I'll call this E of T. And in general, this thermal energy will be less than the kinetic energy, because if it wasn't, very quickly, as we'll discuss, that thermal energy would be converted into kinetic energy. As the material expands, it does, the thermal energy will tend to do PDV work and cause the ejecta to expand. So typically the thermal energy with E of T is less than the kinetic energy. Now, for most of the things we'll talk about, they're going to be, the thermal energy is going to be dominated by that of radiation as opposed to gas. So AT to the fourth, the energy density of radiation, is much greater than 3/2 NKT, the radiation of gas, okay? There's one, luminous red nova are kind of marginal, maybe gas pressure can dominate. For the most part, radiation pressure almost always dominates in everything I'll talk about. And as a result, if you know the internal energy, you can relate that to the temperature based on the thermal energy and the volume of the ejecta. And everything I'm going to talk about, just as my disclaimer, will all be spherical cows, okay? So everything will be spherical from here on out.
Right.
Yes?
The row going as r to the minus beta?
This? Yeah.
Yeah, is that before homology, or that's what you just generically assuming something, or that's what you expect once you're in homology?
For a supernova, I think this is similar to what you get in the inner layers, so near the core, and then there's usually like a velocity above which it gets much steeper. So I think if you explode a star, this would be the homologous profile in the inner parts where most of the mass is.
Okay.
But then as you go towards the surface, as maybe Ram will talk about, as a shock gets accelerated, you get a steeper profile.
Okay.
Right. So I wanted to keep it simple though. So I'm not thinking about the shock breakout emission. Yeah. Any other questions? Okay. So this is the basic setup. So just remember mass, velocity, volume, radiation pressure dominates. Okay. So now I'm going to do, this is again, very, very basic, as I don't know who I have to bring up to speed on this. I just want to talk a little bit about opacities, just so everyone knows what opacity is. So imagine a photon is trying to go through some slab of material of length L, okay? And so there's a bunch of absorbers in that slab, which have some number density, number of absorbers per centimeter cubed. It could be scatterers, it doesn't have to be absorbers. So if each one of those absorbers has an effective cross-section, an effective area sigma, and each one has a mass m, and these absorbers have a mass density rho, which is just their mass times their number density, okay? And so opacity is just the cross-section per unit mass, so as units of centimeters squared per gram. And likewise, the sort of mean free path that a photon experiences, like the typical distance it has to go before it will hit one of these absorbers, It's just, you can convince yourself it's just 1 over n times sigma, or equivalently 1 over rho times kappa. And so when we talk about optical depth across a given distance, it's just the integral of rho kappa ds across that distance. Okay, so if the uniform is medium is uniform, the opacity and density are constant, then this is roughly rho kappa times that length, and therefore it's L over the mean free path. So an optical depth is basically the number of mean free paths across some distance L. Okay, so when you have a material where this optical depth is larger than 1, we call it optically thick, and when it's less than 1, we call it optically thin. Okay, I think everyone knows that, but we're going to be talking about radiation that is trying to expand out of this expanding ball of gas, and so there are different processes that can absorb or scatter light, different sources of opacity. And since we're dealing with an optically thick medium, the relevant opacity is something we call the Roslin mean. It's a particular way of averaging this opacity over the black body spectrum of the radiation of some temperature. I'm not going to talk about that, but I just wanted to emphasize that you can, in general, this opacity is going to have many contributions. So what is preventing photons from getting out of our ejecta? Well, one of the main ones, which is very important, is electron scattering. We're dealing with hot ejecta, so most of the electrons are stripped out of the atoms, and the electrons provide a scattering opacity, which depends, of course, on how exactly ionized it is, how much electrons there are per unit mass, but roughly is a few tenths of a centimeter squared per gram typically. Now, this is for hot ejecta, this provides a sort of baseline minimum opacity. Now, as you go to denser, cooler ejecta, you also have to worry about other things, particularly Kramer's opacity, which is a combination of bound-free and free-free opacity. So this is just showing an example of sort of opacity, these solid lines from opal for different temperatures. At high temperatures, you get basically electron scattering opacity, and at low temperatures, you also get this Kramer's opacity. And as you go to very low temperatures, below 10 to the 4 Kelvin, you also have to worry about H- opacity. And at very low temperatures, potentially molecular opacity. I'm not going to talk much about those. So the other really important source of opacity is lines. Okay, so individual bound transition. A photon hits an atom, excites an atom to a higher state, and then it falls back and re-emits the photon. And so this line opacity is particularly relevant if you have many lines, which is the case for iron, for example, or lanthanides or actinides when we talk about kilonova. So this is just from Pinto and Eastman. This will be conditions relevant to a type 1a supernova, which is a lot of iron, a lot of nickel, which decays to iron. And you see that the lines, basically, there's so many lines that they form an effective continuum opacity in the ultraviolet. And inside the ejecta of a supernova, it's quite hot. So the photons are ultraviolet photons, and their opacity is actually is dominated by this sea of lines. Okay, so we call this line opacity. It's more complicated to calculate. It isn't just a function of density and temperature. You have to account for the fact that the lines are redshifting as they escape the ejecta, and so they have to sort of more escaping out of a line, a photon, to get out of the ejecta. But for our purposes, the effective opacity is typically comparable to that of electron scattering if you have a lot of iron, or it can be less when you're talking about iron depleted supernova like type 2. Yeah.
Sorry, if this is too specific, we can move on.
Oh, please go ahead. Yeah.
Going to press this. Okay. Yeah, I said that if this is too specific, we can move on. I can ask you afterwards. But where does that 7.7 come in hydrogen ionization?
I'm sure it's an expansion.
Is it like that?
Yeah. I think it's some expansion about some Saha equation for the H- abundance. I don't remember actually. I have to go back and look. So okay. It's not exact, but it's like with a nuclear reaction. You're expanding it. It's some exponential that you're expanding about some temperature range where this is like an important source of opacity.
Okay.
I think that's where it comes from. So we could talk about it. Yeah, I have to look it up. I won't know off the top of my head. Okay, so what I want to emphasize though is that the major sources of opacity for what we're talking about talking about type 2 supernova, TDs, luminous red nova. The main source of opacity is electron scattering. When you're talking about type 1 supernova, kilonova, these line opacities are more important. Here I'm talking about the plateau phase of type 2 supernova. And then actually, when you deal with cooler transients, planet, star, star-star mergers, all of these things become important because the ejecta is almost as cool as a star itself. And so you have to worry about all these things, but we're not going to talk too much about luminous red nova. Okay, so going back to our slab, we now want to do it in spherical geometry and ask what is the optical depth through our expanding sphere. So we want to consider some snapshot t after the explosion, where the typical size of the ejecta is v, its average velocity times time. And now instead of through the slab, you can define a radial optical depth. What is the optical depth for a photon to get out of the center? This is like the integral of rho kappa dr out to the center, but then roughly most of the mass is at our ejecta. So we're just going to approximate this as just the average density times some average opacity times the size of the ejecta. Okay, very, very crude. In reality, all these things vary as a function of radius. You should do this integral correctly, but I'm just trying to give you some intuition. So your optical depth through the ejecta to a photon is this quantity. So you can put in for the density m over r cubed multiplied by r and kappa. This is your optical depth. And then r is increasing linearly with time, so your optical depth is dropping as 1 over time squared, okay? So as the ejecta expands, it's getting easier for a photon to get out without interacting. Makes sense. You can ask, okay, well, how long does it take for my photon to get out altogether? How long does it take for the ejecta to become optically thin, for this tau to become 1? Well, you just set that equal to 1. You solve for the time at which tau is less than 1. And this is the time for the ejecta to become optically thin. And if you put in parameters, which are typical of a type 1a, solar mass, as I said, 0.1 centimeters squared per gram is a rough line opacity, maybe a bit higher. You get, several hundred days. Okay, so that's great, but this is too long to be the actual peak time, right? Like supernova are rising on weeks. It isn't rising because the ejecta is becoming optically thin. This is what we call the nebular phase, when it becomes optically thin, and we see optically thin emission from all this hot emitting gas. But it's not what we're after for the rise time. After for the rise time is something called the photon diffusion time. So the idea is that photons are moving at c. The ejecta is moving much less than c. So photons can bounce around a bit and still get out faster than the ejecta is expanding. So they can get out earlier than, they don't have to wait till it becomes optically thin. So we imagine that there are n scatters that are required to move some displacement s out of the ejecta. So we're scattering off one absorber, the other, some kind of random walk. And then we get out a distance, big S, okay? And each length, each interaction will have an average interaction length, which is just the mean free path, okay? So if we square this total displacement vector, vector square, we're going to get two types of terms. One which is si dot sj, where I is equal to j, and si dot sj, where I and j are not equal. If you average over many scatters, this, of course, there's a cosine when you do the dot product. Your scatter or your absorption re-emission direction is going to average to 0. And so s squared is just, you just end up with this term, which is just, there's just n of these, so it's n times the displacement times the mean free path squared. Okay, so that tells you basically, to move a displacement s, you need to move square root of n mean free paths. So the time it takes for a photon to escape this distance s is just the number of scatters it has to make times the time it takes for one light crossing time. And so you can rewrite this using this expression. You can rewrite this essentially as the displacement over c times the displacement over the mean free path, or equivalently the light crossing time of the ejecta times the optical depth. In the specific case where we want to traverse a distance of order r ejecta and the optical depth is our ejecta over tau. Okay, so this is the photon escape time scale, or so-called diffusion time. Okay, so different ways to interpret this. One is to say when a photon is diffusing through an optically thick medium, its effective velocity is basically c over tau. So it's slowed down by the fact that it has to scatter, but it can still get out eventually. When does the photon actually able to get out? So again, we're looking at a snapshot at time t after the explosion, and we can now calculate what is the photon diffusion time through the ejecta at that time. So we know the ejecta radius is growing linearly in time. We know that the optical depth is dropping as 1 over time squared. We multiply this out, and we see that this diffusion time, the time for a photon to diffuse out, is actually dropping as 1 over time. So even though as the ejecta expands, it has to go further to get out, the time it takes is actually going down because it has to experience, many less scatterings as the ejecta dilutes. So the diffusion time to get out is dropping with time. And so when can light get out? Well, it can get out once you've waited for a diffusion time. So once time since the explosion equals diffusion time, then now the photon can get out, or equivalently, once the diffusion time becomes less than the radius doubling time of the ejecta. So you just equate time itself to this diffusion time and solve for the resulting time, and you get this famous expression and I call it the peak time because this is when the radiation gets out, so this is when the light curve is peaking, and it's basically kappa times the mass of the ejecta divided by c times the ejecta speed. Okay. So again, if I put in typical parameters for a type 1a, solar mass, 10,000 kilometers per second, a typical opacity, I get a few weeks, which isn't bad for the rise time of a type 1a. And so this is commonly referred to as the RNet peak time, or confusingly the diffusion time. But it's not. It's a diffusion time at the time when time is equal to diffusion time. So it's not the general diffusion time, which, as I said earlier, which is actually dropping in time. So this is the time where raw radiation can finally get out. So everyone's happy that, okay. But it means there's another interpretation of the diffusion time, and it's also the time where radiative losses take over versus adiabatic losses in this expanding ejecta. Okay, so there's two things that are competing for the affection of the thermal energy in the ejecta. Okay, one of them is the fact that radiation is trying to get out, it's trying to leak out of the box. Okay, this is radiative losses. And the other thing is that the thermal energy is doing work on the ejecta. There's an expansion of the material. It has a pressure. It's pushing on the ejecta, so it's losing energy to PDV expansion work. Okay, so let's consider the radiation losses. So the radiation losses, which is what we see, the luminosity we see, is the thermal energy in the ejecta divided by this diffusion time. Okay, now if I go back, and I can actually write this diffusion time, I can normalize it to this peak time, and I can actually write it as T peak squared divided by T. Okay, you can't see it here, but I can write the diffusion time as T peak squared divided by T. And so then I can write my radiative energy loss rate as basically the thermal energy divided by time times time over the T peak squared. Okay, that's my radiative energy loss. And it must compete with PDV expansion losses. Okay. So that's just the pressure of the ejecta, which, because it's radiation dominated, is just its energy divided by volume, 1/3. So PDV is basically D, and I put my volume, and then I do this derivative. I get dr e dt, which is just the velocity, which cancels. And anyways, I see that my PDV loss term is just the energy divided by time. Okay. So both of these are competing for the thermal energy of the ejecta. And so like I see is at times and before this RNet peak time, it's the PDV loss term that is dominating. My thermal energy is going into work, going into kinetic energy of the ejecta, as if it didn't already have enough. But then after this time, it's the radiation that is dominating. So no longer is the radiation pushing on the ejecta, but it's leaking out to the observer. And so at times greater than PDV, we basically get to see all of the available thermal energy in the ejecta. And it so turns out that if we heat the ejecta after D peak, what we see will basically trace what we're heating because none of it is going into the PDV work. So stated in terms of a schematic diagram, if I have luminosity or power of my transient versus time here, as I said, it sort of rises up to T peak, depending on the mass and velocity, and then it will decay, and then this sort of divides where PDV losses are relevant versus radiative losses. And so if I want to know that, so one thing I want to know, which is what is the duration of a transient, and that's mostly set by this RNet peak time usually. So what is the peak luminosity? Well, when these two things are equal, then where most of the radiation is taking over the losses, then roughly speaking, at this point in time, the peak luminosity is the amount of thermal energy the ejecta has at this time divided by that time. Okay. So then the fundamental question becomes for all transients is how much thermal energy does the ejecta have at T peak? Because that's going to control how bright it gets. So I'm going to go through a few different ways that we endow the ejecta with thermal energy at T peak. One of them is going to be to assume it had a lot of energy to start. And then I'm going to come back to a case where it's continually being heated, and that's why it has thermal energy at T peak. So we'll start with the first case. So this is what I think Lars Bildsen affectionately calls a pure explosion. So this is a situation where you have you explode the star, you inject a bunch of thermal energy at the time it explodes, and then that's all you get. Okay, the initial thermal energy from the initial shock wave is all you get to radiate. But in some cases, it turns out to be enough. So again, we imagine that we have an initial star. We've driven a shock through it when the star explodes. It's endowed that ejecta with an thermal energy initially, which is comparable to the kinetic energy of the ejecta, either that it gets from the shock or will acquire soon thereafter from this PDV expansion. As we already learned, so this is the RDET peak time I just introduced to you. We're going to now scale it to parameters more appropriate to type 2 supernova, which is where this will be relevant. So 10 of solar masses, 5,000 kilometers per second, electron scattering opacity. We see that the peak time of the transient is roughly, and Jared's going to start screaming at me for this being the peak time, but we'll come back to this. So it's roughly 100 days, say, okay, for this parameters. So when does so we have to wait for the ejecta to expand for this radiation to get out. So not all of this initial thermal energy will be available by the time the radiation can get out. So we have to figure out how much it expands up to that point. So we basically take the velocity of the ejecta and we multiply by the RNet peak time, and that tells us how large the ejecta is when finally now the radiation can get out. And you see it's quite enormous, right? The star itself might be hundreds of solar radii if it's a red supergiant, and then it's hundreds of times larger than that by the time the radiation can get out. So how much thermal energy does it have left by that point? Well, adiabatic losses deplete the thermal energy. So the pressure, since this is radiation dominated adiabatic, the expanding gas, pressure goes as density to the 4/3, and since density is dropping as 1 over r cubed, pressure goes as 1 over r to the 4th. And therefore the internal energy of the ejecta, which is just its 3 times its pressure times its volume, the internal energy is dropping as 1 over r. So the amount of energy we have at by the time it expands to some size r ejecta is 1 over the initial star's radius, smaller than what it was during the initial explosion. And as I said, since what gave the explosion its thermal energy is this shock wave that went through the beginning, roughly speaking, the initial thermal energy is how much kinetic energy it has. Okay, so this tells us how much thermal energy it has. So then I can go back to what I just told you a second ago, that the peak luminosity is the thermal energy it has at T peak. And I could basically estimate the peak luminosity. It's just the energy at E peak divided by T peak. I put in these different parameters, and I get this nice expression over here where the peak luminosity is the ejecta mass times the initial star's radius times the ejecta speed divided by T peak squared. And anyways, if I put in the values, I get a number which is a few 10 to the 42 ergs per second for a typical type 2 progenitor of 500 solar radii for typical values here. And so this is, remarkably similar to the, plateau luminosity of a type 2, okay? So roughly speaking, we get the right duration and right luminosity for a plateau, okay? All right, so this is what I called my pure explosion scalings for the peak luminosity of this type 2 supernova, depending on the initial star's radius and the ejecta speed. I get these scalings. You can also express them in terms of the kinetic energy of the ejecta and the mass like that. Okay, and as I said a second ago, these are some example type 2 supernova light curves, which are in this roughly in this range. But as we'll hear from Jared, who will talk about the actual calculation, doing radiative transfer modeling of these supernova, you get somewhat different expressions from this naive estimate that I've done. So the more detailed calculations Jared has performed here. For example, the best fits he finds for the peak luminosity are slightly different coefficients than what this pure explosion predicts. Weaker dependence on mass, weaker dependence on kinetic energy and radius, and rather different dependencies on of the plateau. So what did I do wrong that I didn't get the right answer that Jared gave us? Well, one is that my naive toy model, I assumed that the opacity was constant, okay? Whereas it's not. In reality, as the ejecta expands in a type 2, it cools, the hydrogen recombines, and that drops the opacity. So the light curve is actually controlled by recombination of hydrogen. But the physics of this, at its initial thermal energy that has been adiabatically degraded and is now escaping, is roughly correct. Okay, but caveats be warned, and Jared will go through this in more detail. So the assumption, the critical failure of the model I presented to you is opacity is not constant in a type 2. It changes as the matter recombines. The other thing I want you to notice is that in this pure explosion luminosity is very sensitive to the radius of the exploding star. So if I consider a big star like a red supergiant, even a red giant, it can produce a pretty bright supernova just by blowing up that big star, because it doesn't have to expand very much before it gets to let the photons out. So they don't lose much energy and it gets bright. But if I considered a more compact star, Wolf-Rayet star of a few solar radii in size, its luminosity, according to this, would be very tiny, right? We would never see these things. Well, maybe we would now, but it would be, 10 to the 40 ergs per second or something if this were a solar radius. So more compact stars, you cannot explain their luminosities just by the energy, the shock deposits when they blow up. They need some kind of continuous heating source, okay? And so in many other transients, the thermal energy by the time we reach the R-net peak is not some initial energy endowed by the initial explosion. It's because we're continuing to pump energy into the ejecta by some source of heating of that material. So in general, if you imagine that there's some heating source, Q dot, which is sort of heating the ejecta, and that's what's keeping the thermal energy content high, then the R-net peak definition changes a little bit. It's still how much thermal energy does the matter have at time T peak, but the thermal energy it has as T peak is roughly the heating it gets at T peak times T peak. So the peak luminosity ends up being basically the heating rate of the ejecta at T peak. And for these types of transients, which are powered by a continuous source of heating, this is known as R-net's law, that the peak luminosity is the heating at T peak, but it doesn't, but yeah, this is a case where it's radioactive, or for example, radioactivity or some other source of heating. So then this gets to the question of what powers transients in general, other than type 2s. Okay, what is this source of heating in the center that is keeping the ejecta energetic and luminous and allowing us to see it. And there are really three energy sources which can be heating the ejecta. One of these is radioactivity, so nickel decaying to cobalt decaying to iron. This power is type 1A, and other types of the after the plateau in type 2s, we see this, or our process from kilonova, or I guess in the same category of internal energy sources, I would put recombination. So if hydrogen recombines into neutral hydrogen, that releases enough energy in luminous red nova to make them bright. So radioactivity is one source of energy. Another source of energy is shock interaction, not the shock that blows up the star, but as the supernova ejecta that is already blown up, if it runs into material on larger scales around the star, some kind of circumstellar medium, that shock wave can release, that collides with external medium and slows down the ejecta. That can release thermal energy, which heats the material. As long as that CSM is distributed far from the star, it's effectively like the star is bigger. More of that energy is able to escape without experiencing these adiabatic losses. And then a final possibility is that there's some type of central compact object in the center. If I form a millisecond magnetar after a core collapse supernova, which is pumping in rotational energy, or I have a TDE where there's a accreting supermassive black hole in the center, you could have a central engine powering these events. So I'll say a little bit about each of these cases in turn, and we'll apply the RNet rules we've learned to try to predict their luminosities. So the most canonical case is radioactivity. As I said, the power is type 1A, so this is the decay of nickel 56 to cobalt 56 to iron 56. Nickel decays through an electron capture reaction with a half-life of 6 days to cobalt. You produce an excited nucleus which decays to the ground state and so emits a gamma ray. So the energy comes out in gamma rays. The cobalt then is also unstable with a half-life of 77 days, which decays to iron through the emission of a positron and a neutrino, as well as a gamma ray, or gamma rays. There's a whole spectrum of gamma rays. And so your neutrinos, they basically just escape because their optical depth is 0, effectively. They have such low cross-section. Your positron, well, so your gamma rays, which are the main source of heating, they Compton scatter off of electrons in the ejecta. So they hit the electrons, and because these are MEV gamma rays, that's not elastic, the electron gets a big recoil, and then it thermalizes its energy with the rest of the plasma. So it's effectively turning the gamma ray energy into thermal energy. But the efficiency with which it does so drops because eventually the ejecta becomes optically thin to the gamma rays. In supernova 1A, this is typically around a month afterwards. So there's some efficiency factor with which the gamma rays thermalize their energy in the ejecta. But the positrons thermalize basically very effectively until late times. So if you were to look at the radioactive power from nickel decay channel versus time, this is in ergs per grams per second. It looks something like this. You have the nickel half-life and then the cobalt half-life. I'll come back to this. We'll talk about our process heating next week. It looks like this. But anyway, so if you were to write down a heating prescription for your ejecta, depending on your initial nickel mass, it looks something like this. You have the nickel decaying on its half-life being replaced by cobalt decaying on its half-life. This is the fraction of their energy that comes out in gamma rays, so you have this efficiency factor. And then your positron production from the cobalt is basically always present. And so these are the parameters if you want to use this heating prescription. So let's go to the example of type 1A supernova. So going back to our RNet peak time scale, as I said earlier, if you put in typical mass and velocity and iron line opacity, you get roughly the right scaling for the peak time. Your peak time, you'll notice, is sort of between the nickel and the cobalt decay times. So you're basically past when most of the nickel's decayed, but most of the cobalt has not significantly decayed. And so you get this extremely simple expression, approximation for the peak using Arnett's rule, where roughly for a 1A, the peak luminosity scales as the nickel mass, and with a prefactor of order 10 to the 43 ergs per second for a solar mass of nickel. And so you get, roughly the sort of canonical type 1A luminosity at peak. But of course, there are, as Saurabh has worked on extensively, there are wide varieties of type 1A subclasses, some which produce a lot of nickel and are very bright, some which produce very little nickel and are very dim. But roughly speaking, how bright they are is telling you how much nickel they produce. And then at late times, when you get into the cobalt tail, eventually all the gamma rays are getting out, and only it's the positrons. This takes a while, but only the positrons that are heating you, and then you see this sort of exponential. There's other isotopes that start heating the ejecta at late times as well. But the same physics of 1As can also be applied to the other type 1 supernova. The main difference is that the ejecta mass is higher because we're blowing up a stripped star, so a helium core of order solar mass, 10 solar masses. But there's less iron in the ejecta typically, so the opacity of lines is a little bit less here, but they kind of cancel out the two effects, and you get sort of similar rise times for the type 1bc supernova. So you can again apply this sort of formula to predict the peak luminosity. And as I said earlier, these are coming from compact stars. These have progenitors which are stripped of their hydrogen envelopes, and so that's why we don't see like typically a hydrogen plateau with these events. You're relying exclusively on the radioactivity. But again, you see this kind of roughly linear relation with the nickel mass and how bright they are. And so it's quite a bit bigger spread actually even than typically than type 1As. And then sort of the question is why these events make such wide variety of nickel. It probably has to do with the progenitor core structure, how powerful the shock wave is that's producing the nickel in the core, et cetera, et cetera. But anyways, so you can also understand 1bc's pretty well from that. But let's talk about some of the oddballs here. Okay, so this is peak luminosity. Again, this is a sort of Kishalay type plot versus peak rise. But here focusing mainly on supernova classes. So we have the type 1As and the core collapse. And there's actually a limit to how bright a nickel-powered explosion can be, because if you put all of the ejecta mass into nickel, you can't produce, because of Arnett's rule, you can't produce an arbitrarily short transient with higher and higher ejecta mass. So for a given transient duration, if you put all of your ejecta mass into nickel, there's a limit to how bright you can be from that, okay? And there are several classes of transients which exceed this limit, okay? They're the F-bots, superluminous supernova of type 1 and type 2. And so we know for all of these transients that they cannot be powered exclusively by nickel. In the case of most F-bots, it's probably because, oh, yeah. Yes.
So on the last slide, do the type 2s produce a lot less nickel, or just with the more compact progenitors, you have to adiabatically expand so much that the nickel ends up being the whole show with the light curve?
Great question. Then the type 2s, I believe, typically produce less nickel. So I think Jared can correct me, but they typically produce more like a few hundredths. Yeah, so they're kind of sitting down here. Yeah. So yeah, it's yeah. I think so. So if the type 2s made more nickel, then the nickel tail will go up to meet the plateau at some point. Yeah.
Another question?
Yeah. Oh, yes.
I may have missed this on 2 slides ago.
Yeah.
But the epsilon luminosity equation from 1 slide ago.
Yeah, this one? Oh, 1 slide ago.
Where do those epsilon coefficients come from?
It comes from the physics of how much energy is released when I go from cobalt to iron. Okay, there's a certain amount of energy released, and a certain fraction of that, let's go back to the reactions. Oops. a certain fraction of that energy, which is you can calculate on average, it will depend on the individual reactions, but a certain fraction of that is going into the gamma rays and the positrons. Okay, so those are the two things that are able to thermalize and heat, and the neutrino just escapes, so that's not counted in the epsilon. But it's just nuclear physics basically. So you just look it up if you. There's actually a nice Shri has a nice Will Carney has a nice paper in 2005 where he, in an appendix he goes through all of the nickel stuff, which I found helpful. But yeah, if you want to know more, let me know.
Awesome, thank you.
Yeah, I think Ani may talk about nickel. Okay. All right, so yeah, there are these different classes of supernova. For a lot of F-bots, it's probably because they are compact progenitors, which for some reason have big envelopes when they explode. So some of the F-bots, this may be the equivalent of type 2 emission. But some of the F-bots, I'm not talking about this talk, but some of them clearly have central engines in the center, which are pumping out energy and powering probably why they're extremely bright. But then we have these longer duration things that last sort of comparable in duration to core collapse in type 1As, but just are 100 times, 10 or 100 times more luminous. Okay, these are called superluminous. There actually is a physical. I would say this is the physical justification, is it's above the nickel limit.
Right.
Yes. Yes.
So about this nickel limit,
Yes.
is there an amount of nickel that is like known as a limit, or what it is?
It's basically saying, I have to remember exactly what Cosimo's two lines here are, but it's basically saying, I know what the ejecta mass is roughly from the rise time. And let's say that I put all of that ejecta mass into nickel. How bright can the nickel make it? Okay, how bright can I get just from radioactivity? And that's this limit. And so if you're above that, it's saying that something other than nickel has to be adding energy. Because I can't, if I increase the ejecta mass more, I would make it longer transient, but it's short duration. So that's the essence.
So that nickel limit depends on the ejecta mass, right? But it was not physically possible either to have.
Yeah, it doesn't really physically make sense that the ejecta would be pure nickel, but it's like a theoretical limit. And probably these two lines are probably for, one of them's probably half nickel and the other is probably all nickel or something, but they're both implausible. Well, in type 1A is a significant fraction can be nickel, but in most explosions, we don't expect that, pure nickel explosions. Okay, how are we doing on time? Okay, good. Okay, so I'll go through a little explanations for what, so there's really two contenders for powering these two events. One of them is a central engine. So there's some kind of central compact object which is adding energy. And another is shock interaction. So I'll briefly go over these two possibilities and how they fit into this order of magnitude. You can estimate these things. So there's a model. So one idea here is that your core collapse supernova, and these are probably, these definitely are core collapse supernova in most cases, is producing a energetic remnant. Okay, this could in principle be a black hole, but let's focus on a neutron star remnant. Okay, so I'm forming basically a pulsar in the center, a rapidly spinning neutron star. It's not really a pulsar, but it will be one soon. So I have a neutron star in the center, which is rotating with some angular speed omega. And it therefore has a rotational energy, which is 1/2 its moment of inertia times omega squared. And so if you spin a neutron star as fast as you can at its breakup speed, it will have a rotational energy. You have to look up its moment of inertia. It's uncertain, depends on the equation of state, but within a factor of a few. It will have an energy of a few 10 to the 52 ergs of rotational energy, okay, formed in the supernova. That's a lot of energy compared to the kinetic energy of explosion. It's in principle available to be tapped into. Now you further say that this is a highly magnetized neutron star, so it has a very strong surface dipole magnetic field. And if you recall from electricity and magnetism, if you have a rotating dipole, it emits radiation. That's actually not what's physically going on here. It's actually a magnetic wind, a force-free wind. It's not really vacuum dipole radiation. And it actually doesn't matter if the magnetic axis and rotation axis are misaligned. They can be perfectly aligned, and this object will spin down at roughly the same rate you would predict for E&M for a misaligned dipole. But anyways, so you have this rapidly spinning neutron star, which is spinning down inside the explosion, filling up a sort of nebula, like think of the Crab Nebula, this hot plasma of material trapped behind the ejecta of the explosion. And so the energy that it is injecting into this nebula is basically the rotational energy. You could solve for the evolution of omega as it spins down, and therefore the evolution of the spin down. And so it's basically the rotational energy divided by this spin down time. So this is the time it takes for it to lose half of its energy through rotation, say. And so you could solve for this, and you find that it initially looks like this. Initially, your spin down power is basically flat, and then at late times, this decays as t to the minus 2 in time. Okay, so time since explosion. And typically, so we need for this to be interesting, for these neutron stars to be spinning down on timescales of weeks or months for the supernova or days, we need very strong magnetic fields, like 10 to the 14 or 10 to the 15 Gauss. And that's sort of why people call this, magnetar powered, because magnetars are galactic neutron stars with magnetic fields larger than 10 to the 14 Gauss. So if I go to times much later than this magnetic spin down time, that you can simplify this heating rate, and it just depends on the magnetic field strength and the time itself. Somewhat ironically, at late times, the spin down power goes down if you increase the magnetic field strength. It's spun down faster earlier on. Anyway, so if you assume by magic that this nebula, you're ejecting energy into this nebula, and it somehow gets thermalized with 100% efficiency by the ejecta, then that source of thermal energy is now available to leak out on the R-net diffusion time. And so my light curve from my magnetar-powered supernova would be rising, reaching this peak time, which I've reproduced up here for you, and then decaying away, with the magnetar. And so if you take this spin down power and you plug in the R-net peak time, you get an estimate of how bright of a supernova I could get from a magnetar with particular parameters. And, again, if the magnetic field is around 10 to the 14 Gauss, the spin period is a few milliseconds, I can get luminosities which are substantially brighter than ordinary supernova. And this is one of the going models for the type 1 supernova in particular. So maybe they have these magnetars in the center that were born in the explosion. You could replace the magnetar with the black hole, which was accreting. And if you knew what energy the black hole was injecting, you could play the same game. This has been done. Another possibility, yes.
Do you mind explaining again why L peak is equal to the heating source at the peak time?
Yeah, I can go back. L heat is equal to, right, so why this is true?
Yes.
Okay. It's actually, sorry, can you see me?
Yeah.
Basically, it's sort of, I guess it's remarkably, maybe this is too simplified, but basically the heating energy, the thermal energy you have at T peak is basically your heating rate at T peak times the time you spend at T peak. And I'll explain why this. And so the luminosity is just is just the heating rate at T peak. And the assumption is that at earlier times I was injecting heat into the ejecta this whole time. So I injected, like way back at the beginning of time, I injected a bunch of heat, but it's all lost to the PDV work. because the PDV luminosity is so much larger than the radiative luminosity, it's all lost to the PDV work. And so by the time I get the ejecta has expanded to this radius, the only energy it has is the thermal energy it got roughly in that last expansion time. I'll show you a way to formalize this later. If I had a sufficiently steep heating rate that was like rising really fast to the origin, I could get a situation where it also depended on the earlier heating history. But the point is that any early heating is sort of forgotten at by the time we get to this for most heating laws, including the magnetar one. Sorry, I don't know if that answers your question.
I guess like going back all the way to the point about that the energy, like thermal energy is greater than kinetic energy. Do you mind explaining that again? Like why is it true? Like we have the statement that like
yeah. So if I inject at the beginning, if I inject a bunch of thermal energy into a sphere without any kinetic energy, it will start to do PDV work in that first radius doubling time. In that first time it doubles a radius, it will take that thermal energy and convert most of it into kinetic. And then as it expands again, it will convert, even higher fraction. So like in one expansion time, 90% of the energy will go into kinetic. And then, in 10 more expansion times, it will be 99%. So very quickly, you don't have to expand much from the initial explosion before you've converted all your thermal energy to kinetic. So by the time we get to where the light is getting out, the ejecta has already gotten at least as much kinetic energy as it had. It could have a lot more kinetic energy, but almost all of the initial thermal energy has gone into kinetic after just a few expansion times. So the thermal energy has to be less than the kinetic. I'll come back at the very end to a toy model, which I think captures these things, and you'll maybe in Ani's session, you'll be able to go over how this comes out, or maybe. Yes. Okay. We should talk. It's a little hard to. All right. Okay. So basically, all the energy the magnetar dumped in up to T mag, it's all gone into kinetic energy. So this is a tricky thing. So if I really did have a magnetar of order 3 × 10⁵ ergs of rotational energy, it would necessarily accelerate the ejecta to a very high kinetic energy. And some of these superluminous supernova have more kinetic energy than the canonical 10⁵ ergs, which is one argument people have used to say there is a central engine in the center, because it turns out to be very hard for neutrino-driven explosions to greatly exceed 10⁵ ergs. And there are some of these superluminous supernova which clearly do that. And so all the energy you dumped in at the spin down time has all gone into kinetic. But there's a residual amount of thermal energy which the magnetar has dumped in here, and that's still enough. It's still enough to make a supernova which is brighter than what you get from radioactivity. The other scenario, which is very popular to explain superluminous supernova as well as type 2Ns, is circumstellar shock interaction. So here the picture is that there was some kind of circumstellar medium. So the star itself may be compact or may not, but there's some extended circumstellar medium, which you could think of as like extending the size of the effective size of the star. So as the ejecta goes out, it collides with the circumstellar medium, and that drives a shock into the circumstellar medium, also reverse shock back through the ejecta. And it's the energy deposited by that shock, which probably comes out as X-rays and UV, but is eventually thermalized into optical radiation, which then can diffuse out. Okay. So as an example, if I had a steady wind before my explosion, which had some mass loss rate from the star m dot, and it had some velocity of the wind v wind, it would establish a density profile. If this were the case, it's generally not going to be the case, that you have a steady wind before the explosion. It would establish a density profile around the progenitor star m dot over 4 pi r squared. And then if I said, okay, well, what is the roughly order of magnitude? What is the shock heating? If this is just the shock jump conditions, a shock heats up material to a thermal energy which is comparable to the kinetic energy of the explosion. So if I heat up this circumstellar material with a shock wave which is comparable to the ejecta speed, then my heating rate is basically 4 pi r squared rho times v cubed. So this is not precise, but this is what you roughly get from the shock jump conditions. You're creating thermal energy rho v squared at a rate v shock. So anyways, you get a heating rate, which is basically the wind's mass loss rate times the shock velocity cubed over the original wind velocity of the star. And so I could see that I can get quite substantial shock heating comparable to the luminosity of a supernova if my progenitor star had a very intense wind before it exploded, 10 to the minus 2 solar masses per year, with a wind speed of 1,000 kilometers per second, which is sort of a typical Wolf-Rayet wind speed. If for some reason my star decided to start producing a really intense mass loss rate. So you might be rightfully questioning how, so anyways, the point is, it actually turns out that this shock heating is independent of time or radius, because the 1 over r squared in the density profile cancels the 1 over r squared of the shock, and the assumption here is that the shock is moving out, out to this radius here. What you might question in this type of scenario is, why are you assuming that this is the RNet peak time? Like, doesn't it's not the eject of the explosion that's preventing the radiation. It's the CSM itself, which is defining the rise time. But there are situations where the picture I showed you may be appropriate. For example, if you have the CSM in a disk and the explosion is driving the shock wave into the disk, but in the other directions, the ejecta is just expanding freely, then you can think of the shock as like a centralized source of heating, much like a little magnetar, a centralized source of heating, which then has to diffuse out of the ejecta. So it may still be the case that the relevant time scale to be able to see this radiation is given by the RNet diffusion time scale through the bulk of this material, even though the shock is happening in. And we have, there's reasons to expect in many cases that the circumstellar material around stars may be in a disk. If there's a binary or something that's causing the mass loss, it makes sense it would be disk located. All right, I'm almost out of time, I think, but I wanted to say one more thing. The final thing you can do twiddly estimates on is recombination power. So this is the wimpiest explosions in the universe. Stellar mergers, actually planet star mergers are probably wimpiest, where you produce a bunch of hot ejecta, which is initially ionized, and as it expands, it recombines. So protons gather back their electrons once they cool to a few thousand Kelvin, maybe 6,000 Kelvin, and this releases a Rydberg of energy, 13.6 electron volts. And so you could calculate how much total energy is released by recombination. So if I know my hydrogen mass fraction of the ejecta and I have the total number of protons and I multiply by a Rydberg, I see that there's a potentiality for 10 to the 46 ergs of energy per solar mass of recombination energy. Now, if I say, and this is again wrong in detail, if I say that that energy is released over if I now apply my RNet peak time scale to parameters which are appropriate to a stellar merger, solar mass, a few hundred kilometers per second, and I assume that it's, and this is the tricky part, I assume it's hydrogen setting the opacity, even though it's hydrogen recombining that is controlling the energy release. I get a peak time scale of around 100 days. And so I can do order back of the magnitude, back of the envelope estimate and say, okay, I have the peak, the energy, and I know the time scale. So I can estimate my peak luminosity, and I get some expression like this, and it actually should be, yeah, that's right. And so I get a typical luminosity of order 10 to the 39 ergs per second. And if you look, it doesn't do so terribly bad to explain these luminous red nova, which typically last, in the optical at least, several hundred days. And they have a wide range of luminosities, probably, which is a proxy for how much mass is ejected from the merging stars. Again, in detail, this is wrong because the recombination of hydrogen is affecting one of the dominant sources of opacity. So the light, it's like with the type 2Ps, the light curve, this is not the exact expression. With Tatsuya Matsumoto, we have a more, we think is a more refined analytic estimate for the plateau that accounts for the actual process of recombination, but it doesn't differ terribly from these scalings. So if you want to read our paper for the physics that controls this. Okay, I'm basically done. I just wanted to say, and this Ani will build on this in the module next week maybe, that you could combine all of these things and create a simple one-zone model that encompasses a wide variety of light curves. So basically, it's solving an ODE for the internal energy of your expanding sphere, okay? So you, internal energy is changing as a function of time due to two sinks and one source. The two sinks are PDV losses, radiation, and the one source of energy is whatever heating you want to give the ejecta. And as I said, it's typically as an initial condition, you could say that the ejecta starts with a thermal energy which is comparable to its kinetic. I mean, like a shock that goes through material tends to leave in its wake roughly equal kinetic and thermal energy. And then, you know, just plugging in these expressions, the EDT, the PDV is just E over T. For this term, you have to include a softening. You don't want your diffusion time to become shorter than the light crossing time of the ejecta. So you have to include a softening term here. And the heating there, and as I talked to you earlier, the diffusion time can be written as the R net peak over T, where that's the peak time. And you assume homologously expanding ejecta. And yeah, so then once you solve this and you have the internal energy E of T as a function of time, then you could just divide it. You could basically just read off this term, and that's the luminosity of your transient. And then if you have some more detailed profile of the ejecta, you could figure out where the photosphere is located relative to what I call R ejecta. And then you could even calculate an effective temperature in this model if it's a black body. So this provides you a way to take a given ejecta mass, velocity, opacity law, and you could make kappa a function of time if you wanted, or density and temperature, heating rate, and calculate a basic light curve. And so it can apply to any, you know, you want to put radioactivity in here, fine. You want to put a magnetar in here, fine. So anyways, and I think what you'll find is many of these things I told you in words, you could play and actually see. You could solve this and then see how these two terms play off each other. Yeah. All right. I think I will stop there then. Yeah.
What are the progenitors of the magnetar-powered superluminous supernovae? Do you need something with a small envelope, something rapidly spinning, something also highly magnetized? Like,
why would they have all these properties?
Because you end up with a spinning magnetar at the center. I mean, every supernova isn't a superluminous supernova.
Oh, you're asking what makes them special?
Yeah, like, you know, if I want a long GRB, I need a particular rapidly spinning Wolf-Rayet star. So I'm just wondering what's the analogous thing for the magnetar-powered superluminous supernovae.
I think people would say it's something similar, that the common wisdom is that angular momentum is at a premium in massive stars. And as you know, most are slowly spinning. And there's some reason that a small fraction are rapidly spinning. And those give rise to GRBs. And I think if you said, for some reason, so I would say you'd have to invoke something like that, because to get this rapid rotation, you'd have to say that there's, I think if you look at the masses of the type 1 superluminous supernova, the ejecta masses, they're higher than we infer in GRBs. So there's a mass difference in terms of the progenitors if they are magnetars. So that could be playing a role. In GRBs, the usual assumption is that we're making a black hole for some reason. I don't know if that's true or not, but that would be different. So one of them is some reason making black holes, the other one making neutron stars. Maybe that sort of jives with the difference in ejecta masses. If most of the mass is going into the black hole in one case, and in the other case, it's being ejected because you formed a neutron star. But I think that these things we call magnetar supernova, they could be black. I think they could in principle have black hole engines. They could in principle not be central engines at all. They could be circumstellar interaction. It's just that the trick is that we don't see in many cases any evidence like line emission in these superluminous supernova that would indicate that the matter is colliding with some material. Like usually when you have shocks, you have high energy radiation which produces excited states and emission lines and things, and we don't see those in the spectra of many of these superluminous supernova. But there may be ways like this to hide compact CSM. If I blew these things up and they had very compact CSM, and the ejecta just quickly engulfed all of it, and basically the shock signatures were hidden. And I think that's been the viewpoint of several groups that Nomoto's group, that they could be. So we could be entirely wrong So it's
But you would need something where you lose the envelope while the star is still compact, so that the mass loss doesn't carry away a lot of angular momentum. So something closer to a Wolf-Rayet star than supergiant. But then can you just have a normal magnetic field and then the collapse amplifies the magnetic field enough? Or do you also need something that was like overly magnetized to begin with, plus the rapid rotation?
No, my feeling is that the fact that these would have to be sort of dynamo generated magnetic fields. Okay, so the star is not that magnetized. It wouldn't, but it.
So you just really need the rapid rotation.
So the fact that it's rapidly rotating and highly magnetized are strongly correlated aspects.
Sure.
That one is leading to the other. That's my best guess.
All right, thanks.
This could be relevant to your question, but it's more GR papers, but I don't know how astrophysically relevant is that, but I read that black holes tend to selectively choose ion charges as they accrete, and that might lead to spin-ups. So that might lead to some magnetars then being produced. As Brian said, you need very high spin in the progenitor and then the after core collapse for the magnetar having in the central engine. And so if they do selectively pick up the ions and you have the charge discrepancies, that might lead to the spin up, because the geodesics are like very different for the electrons and ions. Be one of the more GRE explanations for that.
Thank you. I mean, the other thing I will say is that an accreting magnetar spins down very differently than an isolated magnetar. So when we talk about this spin down time, this assumes an isolated dipole, so a magnetar that's not surrounded by any material. Stepping back, the engines of gamma ray bursts require activity on timescales. They require this amount of energy released in minutes instead of day. Okay, I mean that's the main difference. Is a GRB engine is active for very intensely for a few minutes. And a superluminous supernova engine, if that's really what's powering these, is spreading that energy out over a longer period of time. So a GRB supernova actually are not luminous because they have a central engine. They're luminous because they make a lot of nickel. So the main difference between a superluminous supernova and a GRB is the duration of the engine activity, whether that engine is a black hole or a neutron star. And so the one statement I wanted to make is that this magnetic spin down of a magnetar depends on it being isolated. If the magnetar is accreting matter from the star, and you push the Alfvén radius, the standoff radius between the magnetosphere and the accretion flow, if you push that down to the surface of the neutron star, you can enhance the spin down rate by orders of magnitude. So you could turn a superluminous supernova magnetar into a GRB magnetar by just having it accrete matter from the surrounding environments. So I think there's a possibility for some kind of unification where everything is magnetars, and they're just accreting at different levels, I think, with the same properties, the same magnetic fields. It's just one of them is isolated and powers superluminous supernova, and then one of them is accreting. But then if you have an accreting magnetar, then you say, okay, well, it can't accrete too much or it'll make a black hole, so why don't we just invoke a black hole? So anyways, that's sort of my 2 cents there.
Kind of just looking at this illustration here, I'm guessing you have a shock between the nebula and the ejecta?
Yeah.
Like you're inflating with some sort of wind?
Yeah, there's a shock here where the wind collides and feeds the nebula, and then the nebula is driving a slower shock into the ejecta. Yeah, and
so then the peak time comes from when the photosphere goes into that region, and the photon, or not the photosphere, when the photons can diffuse out from this interaction region. Because I don't see how the system can heat the bulk of the ejecta.
Read my paper with Indrik Boom. So basically the nebula is emitting gamma rays, and the gamma rays can actually penetrate this region. And so gamma rays from this nebula go out here, and they can create pairs and heat in bulk the ejecta. So you're exactly right that if it was just, but also the mass coordinate of this nebula can actually go quite significantly out. So if the magnetar has a rotational energy which is comparable to the initial kinetic energy of the explosion, then this mass coordinate can easily be like halfway through the ejecta. So it's not terribly different to consider diffusion time down to the nebula. That's through the bulk. If it was very weak, yeah, I agree. If it was very small nebula, but it does actually eat into the ejecta significantly.
Okay, thank you.
Where are the gamma rays coming from in the nebula?
The neutron star is injecting electron-positron pairs. They cool in the magnetic field of the nebula, and they emit the gamma rays. Okay, Kishalay is gonna drive me off.
Could you please explain again the time scale for the heating term for shock? You were saying that T peak is not necessarily the...
Yeah, I was basically saying that the assumption of this T peak is that the radiation is diffusing through a certain amount of ejecta mass with some speed, right? And all I was saying was, in this picture, the ejecta is in the center, and the shock is actually outside of the ejecta in a 1D picture. So really, the diffusion time should be through the CSM. So the peak time really shouldn't be the diffusion time necessarily out of the ejecta. It should be through the CSM. But what I was saying was, I think in practice, in many cases, the CSM is not spherical. So the ejecta does envelop it. And then it reverts to a case where the photons have to diffuse through the ejecta, because because the ejecta is most of the solid angle. And in not all cases, this may not be the true in all cases. So it may be, I'm justifying why it may be okay to use the RNet time of the full ejecta. Yeah. Okay, we should stop there. Okay, yes.
Why does accretion spin down the neutron star?
Oh, did I say that? It isn't, the accretion doesn't spin it down. It's the fact that it is magnetically braking itself. It has a wind. Yeah, accretion will inject. Oh, it can spin it down, but it generally spins it up. Yeah, that's wrong.
I just wanted to ask one little thought-provoking question. Could you go back to the slide where you had like the different heating mechanisms, radioactivity?
Oh, okay, yeah. The GIF slide.
Okay. So, what if you didn't have any of those? Are there dark explosions out there in the universe that we don't know about?
I would say so. Like every time someone talks about a black hole falling into an ordinary star and it ejects very little material, I always think that. So I think there are cases. At the very least, you'll usually have this recombination of hydrogen. So, but I think there could be very dim things like just like black hole star collisions and nuclei, or star-star collisions are not that bright unless they're huge stars. Accretion-induced collapse makes very little nickel 56, and so it evolves very quickly. And actually, maybe the closest thing though to a pure nickel explosion, it just might only eject 10 to the -3 solar masses of nickel. So, but you're right. I mean, I think if you just, this is what people will say, oh, I slammed this thing into this thing and it should make a bright transient. Not obviously. if you slam things together and there's nothing to heat it as it expands, it will be very dim. So, so I think like star collisions in nuclei are one of the things that I don't think are necessarily very bright unless they're both giant stars. And then they can be bright for the same reason type 2s are bright, because they have this huge shock wave. So I'm sure there are other examples. I'll have to think of them. But yeah, there could very well be. Yeah, I mean, okay, just to finish, when you see this diagram, I hope now you understand the trends that, this is greater ejecta mass or slower. This is greater heating rate. And this is really a lamppost. This is where we see things because they have this miraculous thing, this timing between the decay time of nickel and the Arnett diffusion time. That's why when we see 1As, and you're right, if those two things don't align, there's, there could be a lot of, especially in this corner, things that are fast and dim. Good luck finding them, even with LSST, but we'll see. Okay.
Thanks, Brian, again. So our speaker for the second lecture of the day will be Saurabh Jha. Saurabh is visiting us from Rutgers. So Saurabh did his undergraduate and graduate degree at Harvard, and he was a postdoc at Berkeley and Stanford before starting as a professor at Rutgers. Saurabh works on a lot of thermonuclear supernovae. He's done an extensive amount of work on supernova modeling, and today he'll be telling us about how do we make the connections between what Brian told us in the morning about models, theoretical models of transients, to what observations actually allow us to learn about these models. So with that, so take it away.
Great, thanks, Kishalay. Thanks, everyone, and it's great to see everyone here. This is a really fantastic time to have this event. I'm excited to be here. So yeah, so actually my what I was told to talk about a little bit was actually just more spectroscopy generally. So that's what I'll focus on. Brian and I did not coordinate, but it was great because he actually, you'll see some things that will build right on what Brian talked about. So yeah, I'll talk about spectroscopy of astronomical transients. I'm going to mainly focus on optical plus some UV plus some infrared. I don't know anything about any other wavelengths really, so I can't speak to that. But this is where much of the light for many of the transients comes out. And so this is the kind of optical spectroscopy has kind of been a tool historically for how we classify and analyze these spectra. So here I show you a few spectra going from the optical all the way to the mid-infrared now with JWST. It's been really great. I won't tell you yet what type of supernova this is. If you get bored, you could try and classify this this kind of supernovae, these supernovae, if you will. Don't look it up, but you got to figure it out from the spectrum. Don't look up the names. And then in the background is the beautiful solar spectrum, of course. And so spectroscopy has been really important in astrophysics. I want to bash this person here who gets bashed on a lot in astronomy. This is Auguste Comte, who was actually a fairly famous philosopher. He invented this school of positive philosophy, which actually as scientists, we kind of ascribe to. Basically, he was saying you have to have evidence. If you're going to make some claim, you have to have direct evidence of that claim. Okay, and for him, direct evidence meant like you had to have some of that stuff. If you said, you know, a star was made of calcium or whatever, he wanted you to have some material from that star to show that it was made of calcium. And since he thought that would never happen, he said, you know, on the subject of stars, all investigations which are not ultimately reducible to simple visual observations are necessarily denied to us, right? So we might be conceive of the possibility of determining their shapes and sizes and motions just by looking, but we will never know their chemical composition because we just won't be able to get a sample of stars to study that, right? Our knowledge concerning their gaseous envelopes will know that they exist, but we will never be able to tell their chemical composition or even their density, right? Obviously, important things that we would want to know. We'll never know the temperature of the stars. Okay, and this is 1835. This is before the development of photography, really, and development of spectroscopy. And you know, Comte is given as an example of someone who got it very wrong just before the whole field was revolutionized. And he actually lived through the time of astronomical spectroscopy. So I don't know if he ever, you know, published an erratum or anything like that. I don't know if they did that back then. But okay, so spectroscopy can tell us all these things: temperature, density, motion, and chemical composition, and also sometimes for things far enough away, the redshift, right? So if we want to know the distance, we can also sometimes get that from the redshift. So spectroscopy is quite important, and you know that we'll see why throughout the talk. Okay, I wanted to start with a little exercise for you, though. Here's a picture of a tree. This is the best single tree image I could find that didn't have any copyright issues. So imagine you saw this tree. I don't know, it has some weird thing in the middle, but ignore that. But you know, you saw this tree out there, and if you imagine like all the leaves on this tree just fell straight down, so you know within the confines of the tree outline, fell straight down, how deep would that pile of leaves be? So maybe think about it on your own. Maybe talk to your neighbors for 30 seconds and kind of think about, you know, how deep, you know, would be a pile you would jump into, like, you know, how, I mean, I don't know, meters. Try and even think of what are the right units to even describe the answer to this question. Okay, any ideas? Anyone want to share their thoughts and use the microphones too? Sorry. Apparently, Kishalay tells me these are all going to, your thoughts are going to be recorded for posterity, so it's very important. Oh, I made everyone become quiet. So see. Yeah.
We were talking about it might be a function of like the hemisphere of the tree. If you assume all the leaves just fall down.
Yeah. So okay. All right. Yeah. Okay. Anyone else? Anyone like think of an actual answer, like in centimeters or something like that? Centimeters is not the right unit, but there is a pretty natural unit to use. I won't ask the theorists over here because like that. In fact, this is a problem I stole from Enrico Ramirez Ruiz, who uses them as problem sets. So. Yeah.
We said that the relevant parameter here is if you go along a line, like from the ground upwards,
yeah.
What fraction of the time are you in the air versus on a leaf? And then we're like, well, it's going to be something between a tenth and 100th on a leaf. So we're like, well, it's going to be, a tenth to 100th the height of the tree.
Okay.
There are probably better ways to estimate the fraction there.
So that would, all right. So would you jump into that pile of leaves? If you were so inclined.
Is the question would or could?
Either way, yeah. I mean, I think you could no matter what, but would you do it? Anyone else? Yeah.
We were trying to figure out how many of the total volume occupied by leaves on branches to get the total number of leaves. And I think we would have gotten, converted that to you'd stack them, but we didn't quite make it that far.
All right. Yeah.
We said about a meter.
A meter. I would jump into a meter pile of leaves for sure.
Yeah.
What's the height of the tree?
It's like that big. I don't know. You're astronomers, right? You have an image of the universe, and you need to deduce things from it. Interesting. Okay, so no one has actually seen this problem on a problem site before. Okay, that's okay.
And Enrico Ramirez released this order of magnitude.
Yes. All right, so maybe you should hold off on if you remember the answer. But
I know the Enrico answer, but I disagree.
Okay, good. Yeah.
If you can measure the shadow that the tree casts, then you have some area that leaves can fall.
Yeah.
If you measure the time that leaves fall, then you can, I don't know if you're allowed to see this pile in existence or you have to just think about it. But if you measure the time that it takes for all the leaves to fall, then you can like reverse back out an estimate of the leaves. Although I'm realizing now you have the leaves in front of you, so I think that might be a little cheating. Yeah.
I mean, you could think about it as much as you want. That's for sure. All right. Any other answer? Can I call? Maybe I will call on the theorists to see a theorist's mind at work. Maybe I'll call on Brian for this.
You're calling him.
Any thoughts about? The talk is about transient spectroscopy, so no one has talked about anything about light, for example.
I mean, no, I was about to say I can see the optical depth through the tree, so I see that I don't know, maybe 10% of the light is getting through. So like the column of leaves. No, anyways, that's all I'm going to say.
Okay.
The leaves have to get light.
Yeah. Yeah. Of order unity, right?
So it means that the layer is going to be just a few things.
Right. So yeah, this is what I was trying to get at, and this is, I believe, the Enrico answer. So I want to hear why you disagree with it, right? The idea is that each leaf is supposed to get sunlight, right? And so light needs to get from the sun to the ground, and if there's a leaf in the way, that will get sunlight. And leaves are mostly opaque, right? If you look, you can't really look through a leaf. And so you wouldn't want to be the leaf underneath another leaf, right? That would not be very useful to the tree. Maybe a little of the light does get through. And so, of order unity. But I think probably the Enrico answer, the answer here is that if these leaves fell, it should be a layer of leaves that is one leaf thick. So not a pile you would want to jump into probably, because it would just be one leaf thick. And the idea is they all have to get light, and the light has to travel through this canopy of trees. Okay, so I haven't actually done this experiment, so maybe it's a couple leaves thick, but I would be surprised if it was a meter, right? Like, that would mean a lot of leaves near the bottom that were just not getting light. And you can see the way the tree is shaped, right? Like the leaves near the bottom are trying to get, more access to light as they go further out.
We're a spherical tree.
That we could use our vantage point and say it's the same as.
Yeah. Right, but this is kind of a neat thing, right? Yeah, I would have thought too, like there's a lot of leaves here. It's a big tree. It will be a big pile of leaves. But you know, according to the light perspective, it probably should only be one leaf deep, right? As you fall through. Okay, and yeah, maybe the projection down in the cylinder compared to where the light is coming in from all sides gets you a factor of on the order of a few leaves deep, you know, at most. Okay. So this is really a question about optical depth, and so we heard Brian was talking about optical depth, so I don't have to go in detail here. But the optical depth is very important in spectroscopy. So here's the definition. We saw this before. You can write it as the integral of this absorption coefficient over the path that the light is traveling. Okay, and then again, Brian had all of this. You can either do it in terms of the absorption cross section of the absorbers or scatterers. It doesn't really matter. Or as we usually do in terms of the density of absorbers, the mass density, and their opacity. And again, we heard from Brian about the opacity, so I'm going to zoom through these next few slides about opacity, right? But this defines an optical depth, and indeed that optical depth unity is this important dividing line, right? So we call optically thin for optical depths less than 1, optically thick for more than 1, sometimes a lot more than 1 is optically thick. People have slightly different definitions. But just think of it, you know, transparent means optical depth close to 0. Opaque means, you know, very high optical depth. Okay, so, you know, optical depth can be somewhat you know, it's just a word we throw around a lot, but, you know, you should try and develop that intuition. Okay. So one very important thing is that these coefficients, the absorption coefficient here, the cross-section and the opacity have this subscript nu. Actually, in optical transient spectroscopy, we often use F lambda, so we do things in wavelength units, but these are from my slides when I teach radiative processes, so that's why everything is with nus. But anyway, the point is that these are frequency or wavelength dependent. Okay, so whereas the density of absorbers is whatever it is, the opacity will be generally very frequency dependent. And so you can have the same material be optically thick or optically thin, or even close to transparent or opaque at different frequencies. Okay, so in fact, the air in this room at optical wavelengths, optical frequencies, we can see each other. But if you move to the infrared, you know, the mid-infrared, the air could be quite opaque. So for example, right at carbon dioxide absorption line, you know, the mean free path, which I'll talk about in a second, is, you know, something just like a few meters before. So you wouldn't be able to see more than a few meters in front of your face at those other wavelengths. Okay. All right, and by the way, please stop me. Like there aren't any other really built-in interactive parts, but if you have questions, please stop. I'm assuming that most of you have taken some kind of radiative transfer or radiative processes class and have seen this before. So I just tried to put some of the important things all onto slides just to motivate the spectroscopy discussion later. But if you haven't seen anything, you want me to go slower, I can do that. Okay. So if we want to measure the emergent spectrum from some source, we have this equation of radiative transfer. You can write it as how the specific intensity of the light varies along its path, either in linear space here, this is that way, or if you recast everything in terms of optical depths, which is kind of a nice way to do it, then you get this much simpler differential equation, which says that you have absorption, every optical depth you get, the intensity gets absorbed, and then you have some sort of emission, which is characterized by this source function. Okay, and the units of these specific intensities are the same, for instance, as the Planck function. And so this, you know, for a thermal radiation, that source function is the Planck function. Okay, and so you have emission, Planck, let's say Planck emission, and you also have absorption, and you know, calculate this equation of radiative transfer. It can be more complicated than this, especially if you have scattering, but that's basically the idea. Okay, so the nice thing about this fairly simple equation is that you can see that this specific intensity, it relaxes, as we say, towards the source function. Okay, so if I nu is less than S nu, then this whole thing is positive and the I nu increases. Whereas if I nu is bigger than S nu, then this thing is negative and I nu decreases. And if I nu is equal to S nu, there's no change, right? So you always go towards the source function as you move along the path. As the optical depth increases, the specific intensity becomes the source function. So for example, in particular, if you have thermal radiation and it is optically thick, so tau is large, then the emergent radiation will just be the Planck function. Okay. So that's a nice property. All right, mean free path, Brian talked about this as well. So you can define this just as, the average distance that a photon travels before either being absorbed or scattering. The probability of it going some optical depth goes as e to the minus tau. And so the average optical depth, or it's just another way of describing what the mean free path is an optical depth of 1. Okay, so the mean optical depth for a photon to scatter. In other words, you can write the mean free path as just 1 over this absorption coefficient, or let's say in terms of the opacity, 1 over rho kappa. And this was a equation also in Brian's slides. Okay. So for example, this is a scattering example. It doesn't have to be, it could be absorption. For electron scattering, you have a photon, some free electron. Here's the absorption, the Thomson, the scattering cross section in terms of sigma. So you just need the number density of free electrons. You multiply those two together. That tells you the optical depth. Or you can do in terms of the opacity. And we saw this again in Brian's slides. That was the opacity for pure ionized hydrogen. It depends on how many free electrons you have per unit mass, exactly what that number is. Okay. And so in the interstellar medium, this is, n is quite low, 1 particle per cubic centimeter. And so photons can travel quite cosmological distances before getting scattered. But in things like supernovae or in the interior of the sun, where the density can be quite high, okay, then obviously a photon inside the interior of the sun only travels a little bit before it gets scattered. Okay, so it can be a huge range for these mean free paths. Okay, and then this, I was going to spend a bunch of time on this, but Brian had all of this in his slides, so I will skip through this. But there are many sources of opacity. The important ones for today: electron scattering, and then we'll talk about bound absorption. And Brian was able to take this Rosalind mean and integrate over frequencies with some weighting and some hand waving. But for spectroscopy, we can't really do that, right? We want to know the difference between the opacity at some specific wavelength where there might be a line, and so that might cause a feature versus some other wavelength. Okay, so for the spectra, we have to do it, keep track of the opacity at all these different wavelengths. Okay. But if you don't care about that and you just want to integrate, that's what these tables are. These are these opal opacities that Brian also showed. At high temperature, basically all the atoms are ionized, and so there are no bound transitions, and so you basically just get free electron scattering. But as lower temperatures, and depending on the density, et cetera, and you integrate over the opacity over frequency, you get different combinations of electron scattering, free, bound free, and especially those bound absorptions where you have to just keep track of all your chemical species, all the possible transitions, which ones are populated, et cetera, and that sets what you see. Okay, so for example, this sharp edge is just due to this very high opacity of iron lines, actually, as Brian mentioned in his talk. Okay, and where are these lines? Well, I assume you've taken enough quantum mechanics, you've seen stuff like this, but I like this representation. All of these elements have different lines. They also have different ionization states, right? So the different number of electrons changes all the levels. And so you have to keep track of the element, its ionization state, all the possible levels, et cetera. There's a lot to keep track of, especially at the wavelengths that you might be considering. If you can integrate over it, it makes it somewhat easier. And Brian talked about like that continuum of lines when you get to stuff like this, and then that can kind of help you. But if you want to look wavelength by wavelength or frequency by frequency, you just have to keep track of all this, right? So that's why I'm not a theorist, because I don't want to keep track of all that. All right. One interesting thing is actually like if you ask someone, why does the sun have spectral lines? You often get to this convoluted answer where it's like, okay, well, it's hot in the inside and there's black body photons coming out, but then sometimes there's some material and it will interact and it'll get absorbed. And there is a correct way to describe it that way, and you can use the equation of radiative transfer to do it. But actually, I like this way better to describe it. And it's just that you're seeing black body spectra everywhere. You're always seeing black body spectra. Why is the spectrum not a black body? It's because you're seeing into deeper or different depth layers. Okay, so for this idealized stellar atmosphere case, you can just assume that the optical depth is really high, which it is for stars. You just have to go far enough in. But what's different is that this absorption coefficient here, okay, is going to be high when you're at a line transition, and it's going to be low when you're in the continuum, let's just say. Okay, and so what that means is the optical depth. Turns out you can show that you see into a star roughly up to the optical depth of one surface. Okay, and that makes sense if you think about it in terms of the mean free path, right? The photon is going to scatter one last time before it comes out to you. And how far into the star did it scatter? Well, on average, it's going to be one mean free path in. Okay, so optical depth of 1. Okay, so you see into the tau equals 1 surface. So you set tau equals 1, and that's an integral of this absorption coefficient over the path length. Okay? In the continuum where alpha nu is low, you have to integrate for longer. You have to go deeper into the star before tau becomes 1. Okay? If alpha nu is high, like in a line, you don't have to go as far. So this ds will be small, the integral ds will be smaller path length, and you'll get to tau equals 1 higher up in the atmosphere of the star. Okay? Now, if deeper into the star is hotter, that means in the continuum, you'll see a higher black body, a hotter temperature, and in the line, you will see a cooler black body. And so that's what you see here. In the continuum, this is actually for the Earth, but so let's multiply all these numbers by like 20. But anyway, you know, in the continuum, you see a 300 Kelvin black body here. But in the line, because you only go so far in, you see a 220 Kelvin black body, and it looks like an absorption line. Okay, and of course, you can describe it as an absorption line, but I like this version better. It's just 2 Planck spectra, you know, and here it's the line Planck spectrum, which is a cooler Planck spectrum, so it's lower. And then here it's the continuum Planck spectrum, and it's hotter because you're seeing deeper in. And that was what creates the appearance of an absorption line, but you're really seeing Planck spectra everywhere. Okay, and so that's another way to think about the way stars work, and it works generally okay for astrophysical transients too, as long as you have a photosphere, as long as you're always reaching this tau equals 1 surface at every wavelength, and things are in local thermodynamic equilibrium, stuff like that. But you know, this is another way to think about what the spectrum that you see actually is coming from. And I find it easier. You don't have to keep track of individual photons. It's just Planck spectra, and it's just a question of how far in you're going. Okay, hopefully you've all seen something like this, but it's a interesting, different way to think about it. Let me pause there for questions. Okay, I won't go into the details of why the line opacity is higher. You can actually calculate all the line opacities. I mean, someone can, I can't, but someone can do it. You have to use the dipole operator and wave functions and stuff like that. It's all here. I'm going to skip all this, but okay. So the line strengths depend on the atomic physics. There are wave function integrals with the electric dipole and higher order operators. You can look it up in the textbook how to do this. This is all from Rybicki and Lightman. It's in there. You can calculate what the line strengths for all these different lines can be. You have to look up some things. So you get these Einstein coefficients. You go to things like the atomic line list online. It will tell you what these Einstein coefficients are. Okay. So, and they're all connected to each other. They depend on various things, the connection. But anyway, so once you know one, you know them all. And so you can just look up what they are for a given line. And then, you know, you can write it in terms of the Einstein coefficient. You can write it in terms of something called the oscillator strength, all different ways to do it. But anyway, that tells you basically the strength of that line from the atomic physics part. Okay, so it turns out the highest Einstein coefficients you get is when the transition is allowed or permitted by the electric dipole rules, the electric dipole transitions. So that leads to certain selection rules. Then there are some forbidden transitions which are not allowed by the dipole transition rule. Like you have to use higher order operators to describe the field before you get some non-zero probability of those transitions happening. Okay, so when the lines are in such a configuration that the two states have, you know, are allowed by these selection rules, you can get a relatively high rate of emission here. This is the Einstein A coefficient. And so, for example, here's nitrogen 2, and remember N2, that means singly ionized nitrogen. There are these two levels. Here's the wavelength, 1084 angstroms. It has a fairly high Einstein A coefficient, something like 10 to the 8th per second, meaning that in 1 over that time, that's the typical lifetime. So if you have an electron in this excited state, it will decay to this other state in that short period of time. Okay. And that's because those wave functions, you multiply by the dipole operator, which is just Q times R, anyway, E times R, and then you do the integral between the two wave functions, you get some non-zero value. Okay. But sometimes you have states like this where when you do that integral, you get 0 for the dipole operator. And so you have to use either the magnetic dipole or the electric quadrupole or some other higher order version. And then so you generally will get a much lower value for this Einstein coefficient. And so we call these forbidden lines, and you can see there's 11 orders of magnitude difference between those two things, okay? And the reason they're called forbidden is because we just don't see them in terrestrial conditions. In terrestrial conditions, this kind of transition will happen. The electron will just drop and emit a photon. But in this kind of sense, the electron is kind of stuck there for a quote unquote long time. I mean, 10 to the minus, 1 over 10 to the 3 seconds is not that long. But anyway, it's kind of stuck there. And what's going to happen is most likely some other atom, some other molecule, whatever, is going to hit that atom before it can radiatively decay. And it will just have it will lose its energy from collision of kinetic energy rather than radiate a photon. Okay? So collisional de-excitation is usually what prevents us from seeing these forbidden lines on Earth. But if the density is low enough and there's nothing around to hit, right? So if you can go 1,000 seconds without hitting anything, then there is some reasonable likelihood that the electron will decay and emit this quote unquote forbidden line, okay? And space is nothing if not low density, oops, wrong way. So in fact, in astrophysical situations, we often see these forbidden lines, okay? In generally low density environments, okay? So that's true in the interstellar medium, but it's also true in supernovae. When the ejecta thin out over time and the density goes down, that's when you see these forbidden lines popping up and being an important coolant, a place where you get radiation going out, especially because the chance of it getting absorbed, because the A coefficient is low, the B coefficient is also low, the chance of it getting absorbed is quite low. So once you get this forbidden line photon, even though that material is there, it's not going to absorb it very readily. And so that those lines generally just escape and carry away energy.
So these would be like a very late time?
Generally speaking, yes, and I'll show you, yeah, so generally at late times, Brian mentioned as you enter this nebular phase, and he showed you the calculation for when that would be, like 250 days for a typical, 1A, let's say, you would expect then the lines to be dominated by forbidden emission. In fact, that's what we see. Exactly. Okay, so there's atomic physics, different line strength, but there's also temperature, density, various other things, right? To have an absorption, you need the electron to be in the correct state for it to be absorbed. Okay, so if you're looking at a particular line. And so, for example, this was all worked out at the turn of the century for things like the Balmer lines of hydrogen, right? So they start from the n=2 level of hydrogen up to 3 or 4. Okay, and so if you want to figure out, well, where would you get strong Balmer lines? It turns out a very narrow range of temperatures. First of all, you need the electron to be in that first excited state. That requires some relatively high temperature to get the electron excited. For example, in the sun at 5,700 Kelvin in the outer atmosphere, it's not hot enough to excite the electrons appreciably to the n=2 state. Okay, so that's what's shown here. There's the Boltzmann factor. Okay, what fraction of the electrons are in the n=2 state. Problem is, if you heat it up enough, then it's actually easy just to also ionize the electron completely away from the hydrogen. And so you use the Saha equation to figure that out. And so here's the ionization fraction for neutral hydrogen or ionized hydrogen at densities like in the atmosphere of the sun. And you can see, like, once you get up about 15,000 Kelvin, all the hydrogen is ionized. Okay, so too low, you don't have enough excited hydrogen. Too high, it's too ionized. And so combining those two effects, you get something like this. There's a sweet spot for where you would expect strong Balmer lines that depends very sensitively on the temperature, and where you expect them is around a temperature of 10,000 Kelvin. Okay, and if you remember from so line strengths don't only depend on the atomic physics of these lines, but also temperature, ionization. Ionization is somewhat controlled by the electron density, et cetera. So all these things can play a role in which lines you see. Okay. And of course, this was very important in the history of astronomy and the study of stellar spectra. So you remember Annie Jump Cannon, someone who is revered in these halls. She put the stellar spectral classification, which was classified by the strength of Balmer lines. So the A stars had the strongest Balmer lines, the B stars the next strongest lines, right? She put them in the right order in terms of temperature, and then the A and B stars are kind of in the middle, and it's because of this reason that you get strong bomber lines at a temperature of 10,000 Kelvin. Okay? And for a long time, actually, there was this idea of like, what was the sun made of, right? To answer Comte's question. A lot of people actually at that time thought the sun was just like the Earth. There's some hypothesis, I forget the name, it's like terrestrial hypothesis, something like that. But anyway, the idea was that the sun's composition was the same as the Earth's composition, just turn up the temperature to 5,700 Kelvin. That's what it would look like. And it kind of makes sense. If you look at the sun spectrum, there's iron and calcium and stuff that we see in the crust of the Earth as well, right? And so that was the idea, that the composition of the sun and the Earth were the same, just the only difference was the temperature. Okay? And it took Cecilia Payne-Gaposchkin to understand that that's not the case, right? That the sun is like these other stars, even the ones that show the strong bomber lines. The sun also has a ton of hydrogen, mostly hydrogen and helium. Okay? It's just those are not strong at those temperatures because of these atomic physics effects. Okay? And so in fact, Cecilia Payne, who kind of showed that the whole universe is made up of hydrogen and helium, right? This is from all of this atomic physics that was developed. So, Annie Jump Cannon is kind of well known, I guess, in astronomy. I think Cecilia Payne is less even. She is someone to know. She really showed that the universe was made of mostly hydrogen and helium, and all stars basically have the same composition, at least to 0th order. All right, let's switch over to like what makes things different for astrophysical transients. And again, thank you, Brian, for setting the stage for this so well. Okay, so we have this idea of homologous expansion. The way I like to think about this, I always use these analogies, which are actually bad because I believe the analogy more than I understand the physics. And so this is like an observer's curse, I guess. I don't know. But I always think like, okay, you have a marathon, it's starting out, right? Let's say just everyone runs at one speed, one fixed speed, right? So it's starting out, it's chaotic, people bump into each other, but eventually you find your speed, you find your people who run at your speed, and the people who are running faster than you are ahead of you, and the people who are running slower than you are behind you, and everyone just runs from then and doesn't run into each other, right? So this is why we think there's homologous expansion, is like whatever jostling and bumping has happened, it's all happened, and now everyone is going to be able to proceed smoothly. And so that might just take a few seconds or a few hours or a few days to get right for different supernova type explosions. But once you have that, this is a pretty typical assumption for basically most astrophysical transits, that the ejecta are expanding homologously. Okay, so you can just say that R is equal to V times the time since the explosion, or the time since homologous expansion was, reached. Okay. So rather than write rho of R, because the density at any place will keep changing because it's different material at that place. The composition will keep changing. At some fixed R, there will be different material there over time. It's much more natural to use V as your radial coordinate. Okay, and so then basically your composition is going to stay the same because you're just with all the the people who were traveling with that speed, all the elements that were traveling with that speed. That's just going to stay the same throughout. Okay, and so your density will change. Okay. And so you would, as Brian said, that the density is just going to go as t to the -3, okay? And then as a function of distance or radius or really velocity now, it goes as some index minus beta, which, as Brian showed, for the inner layers, that might be close to flat. For the outer layers, it can be quite steep, like -7, -8, something like that for beta, or 7 or 8, okay? But you have this homologous expansion. It's also, people like to think of it, this is like a kind of a mini Hubble law. I mean, people get confused, right? Like the Big Bang was an explosion. It wasn't, the whole universe expanding. But anyway, it's still the same V proportional to R, like in Hubble's law. And so you can kind of think of it that way as well. Okay. So one important thing for this is that the density, optical depth, everything that we said that the spectrum depends on is going to change with time. And so the spectrum of an astronomical transient is going to change with time. So unlike the stars, where everything's kind of static, right, we have this dynamic part as well. Okay, so just to show you what this looks like. So here is, and by the way, I stole many of these slides. So actually right now, the person who was supposed to give this talk was Wolfgang Kurtzendorf, who is often here. He's a professor at Michigan State, but he also spends a lot of time here in New York, comes to the CCA a lot. But actually right now he is running a summer school of his own on this TARDIS spectral radiative transfer code. And so he was the one who, you would have gotten the better talk from him. So, but he's giving it somewhere else. So, but he did send me some slides to show. So, anyway, so here is our astrophysical transient early on. And what's highlighted here is there's like a red, let's say tau equals 1 surface. Let's call that the photosphere. That's the typical depth that you're going to be able to see into. Okay? And so here it is, early on. Later on, the whole thing is expanding. In fact, even the photospheric radius is expanding. Okay, continuing going on, et cetera. And actually, what starts happening is the density is decreasing. And so remember it was the integral of alpha ds, and alpha was rho times kappa. Rho is going down as t to the -3. Kappa, the opacity might also be changing because the temperature is changing, et cetera. The composition might be different in different layers. Okay, and so what's happening is actually to get to optical depth of 1 at late times, you have to go further in. And so we say that the photosphere starts to recede into the ejecta. Okay, it's moving to lower velocity material. You're seeing further into the ejecta. And then eventually, as again, Brian showed you the calculation for, you can calculate when this happens. Eventually, there is no photosphere. All the way through the ejecta, the optical depth is less than 1. There is no tau equals 1 surface. And now you're going to see right through the whole ejecta in what's called the nebular phase. Okay, so we have this dynamic aspect to astrophysical transients, and we have the density and temperature in general decreasing with time. Okay, there's another thing. Is even if you just want to say, okay, I don't care about the time evolution. I have a spectrum at maximum light. I want to understand that. I want to model that. Okay, there's another problem. Okay, so if you think about, so there's some photon. Let's say it's a UV photon, 4,000 angstrom photon here. Okay, being emitted from somewhere deep in, and it's going to come out. So from our point of view, an observer, we're at rest. The explosion is happening, but we're at rest with respect to the center of the explosion. What that's going to look like is, okay, this 4,000 angstrom photon is just going through the material. Maybe it'll interact, maybe it won't, maybe it'll get out. Okay. But from the point of view of the material, and if you're doing a model and you have to calculate the interaction between the photon and the material, it makes sense to work in the frame of the material, right? You don't want to like have the photon moving and the material moving, like, I'm sure you learned in some class, like make something not move. That's the right frame to work in, right? And so if, in the observer frame, like, yes, it looks like that, but from a frame where you're moving with the material, okay, well, what does that look like? Okay, so now, right, you're all these runners running in a race and you're going to interact with the photon, then someone further along with you is going to interact with that photon, right? But the person further out, they're moving relative to the center of the explosion where the photon was emitted. So that from their point of view, they're moving away and it's faster and faster as they go further and further out. So the photon is just going to get more and more redshifted in their frame. Okay, so someone right next to the center, right, will see the original frequency of the photon. But as you go further out, right, this photon from that point of view of the material in that layer is going to get redshifted. Okay, and so it might have been a photon that was not in a line transition somewhere over here, but as you move in the different layers, suddenly it might be a place where there is an absorption line, right? And so this becomes quite complicated. There's going to be line interaction somewhere. You have billions of lines. You have all these photons. They're all redshifting, right? To keep track of this is pretty complicated, even at a single epoch, right? So this is like moving, but even a single stationary epoch, like, the different layers are at different speeds. And so it looks like the photons have different redshifts, okay? And so moving, but stationary in time. This is kind of like a model assumption, right? So this is this snapshot technique. And even though we're looking at one epoch to try to calculate the spectrum, we have this issue where, the same photon might interact with the same line at different places because of this redshifting effect. Okay, that makes it complicated. You have to make some kind of approximations. There's a line profile function that was on one of the slides before. That's usually kind of complicated. There's broadening mechanisms, et cetera. If you wanted to do that properly and also do it in 3D and also include polarization and various other things, like it's just too much for typical codes. And so typical codes will use something like this, which is called the Sobolev approximation. You just imagine the interaction happens when the photon is at the frequency, right at the line frequency. And you ignore any line profile broadening, and someone has shown that that works pretty well. Okay, so you only look at one place in the ejecta where that photon has the right frequency for that layer to interact with the line. Okay, so that can help you. Okay. But there are many lines, so the same photon could potentially interact with many lines on its way out. Okay, so here's an example of that. There's also continuum opacity from the electron scattering. That there's always a chance of that at every layer. So here's like how the optical depth builds up. There's a chance. Oh, you got an electron scattering. Okay. Oh, here's a place where you got a strong line interaction. So there was a huge optical depth. Yep, you got an interaction. Electron. Yeah. So you can have this. The same photon is going to have multiple things before it gets out. Okay. So that's something you have to keep track of. All right, another thing is, again, even in the static one epoch, not doing the whole time series of the spectra, so you may have seen this, you get these P Cygni line profiles. Okay, so named for a star. So there's a star in the constellation Cygnus the Swan, P Cygni, it's a variable star. It has these kind of weird line profiles, and now people understand that it has a very strong wind, and so you get the same kind of effect. But if you want to see real P Cygni line profiles, don't go to the star P Cygni, go to astrophysical transients, which are moving much faster. Okay, and then you get this kind of thing. So who's here has seen P Cygni profiles and stuff? I've been working with P Cygni profiles a lot with my career, but I have to go back and remind myself, because it's easy actually to get confused, like what the emission you're seeing is. One really nice thing is that if you observe as a function of wavelength, you can just convert that with the Doppler shift as a function of velocity. And then in this nice spherical assumption, so let's say you're the observer here, when you do the Doppler shift, you only see the radial velocity. So you only see the component of the velocity in the line of sight direction. Okay, and then you can ask, okay, where in the sphere are all the material, emitting material, with the same radial velocity? And the nice answer to that is, well, it has to have the same velocity in the, let's say, x direction. Okay, and so it's going to be a slice through. Okay, so all of the material at one slice through this picture will all show up at the same wavelength. So that's really nice. It's like a scan through every wavelength that you see is like a scan through the profile. Okay, and then you're going to have, now the thing is unresolved, so you don't get to see the different parts of it unless it's very local. So typically it's going to be unresolved. So you're going to see emission from over here come to you, emission from over here come to you. Then here, because here's where the photosphere is, here it's optically thin, right? You don't intersect that tau equals 1 line. Here you do, you hit it, that's the photosphere. Okay, and we can assume that it's just a thermal spectrum at that point, right? And so then you're going to have this normal situation like in a star, right? You're going to have a hotter photosphere with material above it, so you're going to get an absorption from here. Okay, and so you put it all together, you add it all up, all the emission that you see. Again, you can do it slice by slice. That makes it easy to get the profile. You get this characteristic P Cygni profile. The absorption is blue shifted because it all happens here. The emission is actually centered at the 0, and then it even extends to, you get redshifted emission from up here and down here, so that's material moving away. And so you can get this shape. Yeah, question there. Yeah.
So how do you compare with that X slice spatially?
You don't, right? So if you assume it's spherical, then you can just do this, right? But even then you're integrating over everything you see, and so you have to assume that it's uniform or make some assumption about what it's like. But yeah, this is the spherical cow assumption. You have to assume something about how you want to.
Do you have to have like an instrument that goes around the source or something to get more sense of where it looks like?
Well, if you could resolve it, so if it was close enough such that you could map out the emission part separately from the absorption part, then you could get a lot more information. But we just generally don't have things that are close enough. We resolve the sun, we resolve some very giant stars, but basically nothing else, right? Yeah. Yeah.
I'm confused about this X thing. Can
Yeah.
you explain it again?
Yeah, sure. So there's a direct connection between the radial velocity and the wavelength observed, right? Just from the Doppler formula, right? So delta lambda over lambda is equal to V radial over C, right? So for things that's moving away from you, it's going to be redshifted to a longer wavelength. Things moving towards you, blue shifted to a shorter wavelength, right? So this axis, which is the velocity along the line of sight, you can convert this directly into a wavelength axis, right?
Okay.
Yeah, and so you just look at the line profile as a function of wavelength. It's going to look just like this. Yeah. All right, I think there was a question over there. Yeah.
Oh, I had some question about the SFC. So as a result of the So like when we're looking at the sphere, are we like actually slicing vertically, or like are you just referring to the like lower part of the diagram?
So we are slicing, yeah, we're not slicing it, we're slicing it in up and down lines. So if you think about, okay, the material that's moving, so let's say all this material is moving at some speed, and actually it's moving at multiple speeds to, with the homologous expansion, the closer you are to the center, the slower the speed and the closer you're to the edge. But let's say there's some maximum speed, I don't know, 30,000 kilometers per second. Okay, so it's moving out this way at 30,000 kilometers per second, it's moving this way at 30,000, this way. Where are you going to see that 30,000 kilometers per second speed? Well, you only get the radial velocity component from the Doppler shift. So you're only going to see that bluest part right here, the material that's moving directly towards you. And that's going to be right here at, let's say, 30,000 kilometers per second, whatever it is. Okay? What about this material? Well, yes, it is moving at 30,000 kilometers per second, but from your point of view, that motion is all in the plane of the sky. And so there's no radial velocity. So the emission from this material right here is going to come at the rest wavelength. And so the idea is what you do is you take slices, vertical slices through this structure, and everything that you get at that one slice, that's the emission that you get at that wavelength. Yeah, good.
I'm trying to see with my pen.
Yeah.
The bottoms.
Thank
you. I'm sorry. I'll ask it. I was holding up my pen to see if the bottom of the absorption trough lines up exactly with the photosphere.
I don't know about it exactly, but in fact, that is what we usually use to measure the photospheric velocity, is the bottom of the trough. And I'll show you some movies of this, and we can check to see if it's always exactly there or not. But I think it's pretty close. Yes. Yeah.
One more.
Yeah. No. That's. Yep.
You get slices through the.
Sorry. Do you get slices in depth too, or just the very front image?
You get every depth has a different wavelength, right? Because it has a different radial velocity.
Okay.
Yeah. So you get the whole thing.
With
right?
red, you can differentiate with redshift at which depth you're
Yep.
at.
Yep.
Okay.
Exactly. Right. You can't differentiate in the other directions because it's all unresolved, but you can get the depth through. Yeah. Now there's some material you don't see, right? It's blocked. So, you have to combine that with the radiative transfer of what light actually gets to you. Yeah. Great. Okay. So that's one version. I have many versions of this. Good. So again, so you can see these different slices through the ejecta, and that leads to the line profile that you see. Okay. Blue shifted absorption, net emission. Okay. And the sum is this profile. Okay. All right. So there's some things you can look at these. There's some movies here. So here is, for example, increasing the photospheric velocity. So that's the velocity of where the tau equals 1 surface is. Okay. And again, you can see that does change where this peak, the trough of the absorption is as you increase the velocity. Okay. And so indeed, this says it's exactly at that. So someone has done the calculation. Okay. Here's another one. And then here's a paper. Yeah.
Question. I've always been confused by this particular animation, which is so the maximum velocity of the absorption never lines up with the photospheric velocity. So what is the photospheric velocity like in a physical sense?
Yeah, so the photospheric, that's where the tau equals 1 surface is, right? But when tau is less than 1, there's still some chance, e to the minus tau, of absorption, right? And so what happens is, right, you will still get some absorption until tau is so low, way out here, that there's essentially zero chance of absorption. So that sets this, how that goes. But it also depends, how is the density changing with velocity, right? How is the optical depth changing with velocity? That's going to set the shape of this blue wing of the absorption profile.
So does that correspond to the physical velocity for the majority of the ejector?
It's roughly the tau equals 1 surface, right? So it all depends where the mass is, what is the opacity, yeah. But it is the easy thing to measure this trough. And so that is what we call the photospheric velocity, right? So yeah.
Yeah, so I think I'm asking literally the same question, but
Yeah.
I need to use different words. So when observers show me a P Cygni profile for a transient, and I want to estimate what is the objective velocity, maybe it's is it the shoulder as you're turning into the absorption feature?
So usually what people do is they say the emission is at the rest wavelength,
Yeah.
and the absorption is at the photospheric velocity, and they will take the difference between those two. So these two lines here as that's the photospheric velocity.
And so maybe at early times, the photosphere is farther out.
It will be a higher thing, and I'll show you examples of exactly that, right? So yeah, when everything is more compact, right? So the density is higher. You think from the outside in, when do you get to optical depth of 1, right? And so earlier on, the density is high, so the absorption coefficient rho times kappa is going to be high. You don't have to go very far in, so you're going to hit the photosphere. So this black circle would be a bigger fraction of the material, and you're going to hit the photosphere at some higher velocity. And so this will be further out, right? So think of this movie backwards, as over time, it will be further out, and then later on, if the photosphere is receding, it would move in. But actually, if you saw in this animation, right, actually the photosphere can increase and recede. So here, the photosphere actually got bigger. It went further out into the ejecta, and then it receded later. So it can change both ways. It depends.
But V goes as R, so I should have the most stretched out P Cygni line when the photosphere is at larger radius.
Yes. Yes. Sorry, I know. They're like the people who know how to do Keynote and get to the right slide.
So photosphere is non-monotonic in radius, but it's always monotonic in velocity, right? So so it's always going to lower velocity, right? But in radius, it moves out and moves it, I think.
Okay, yeah,
I think so.
It may not change very much, though.
Capacity is something weird.
Yeah.
So in supernova, they use like this FE2 line to infer the photosphere radiation. I've always been, I never knew why.
Yeah, so I don't really know why either. Like other than, so what's going to happen with different lines, right? You're going to hit tau equals 1 at different places, right? So, there's no one photosphere. It depends on what frequency you're talking about, right? So different line. So, so your question was, where is most of the material? I want to know where most of it is, right? So I believe they use that line because from simulations, they find, oh, the silicon line is too strong. It always is too far out. And so you just get too high a velocity. That's not where most of the mass actually is. But if we use this weaker iron 2 line, that gets you closer to where the more average mass is, right? So that's something someone has calibrated based on looking at some simulations. So yeah, I don't think there's some deep physics to it. It's just like, oh, that's a weak enough line that you get it at the place where the actual average photosphere really is for them. Yeah. Okay, and then you can do more things. So this is, again, changing the photospheric velocity. You can change the total optical depth through the material. Okay, so that sets kind of, I said you always see the tau equals 1, but it can be more complicated than that. So that sets that. You can change the density slope, the beta parameter, how the density changes with velocity. That's going to change the line profile. You can change the continuum, the temperature is going to, so making the line different as well. So all these things are, again, and all these things are happening. And again, this all assumes spherical symmetry. If it's not exactly spherically symmetric, then of course it's going to change the line profile also. All right, so these are some nice graphics from the TARDIS people. Okay, so there are people, there are simulators who go out and actually blow up a star, okay, before it's homologous, so they get to see all the, everything happening. And then within a few seconds or a few hours or whatever, it becomes homologous, and then you can do your radiative transfer through that, okay? So for example, for a type 1a supernova, it might look like this, right? So you've blown up the star, you started with a carbon-oxygen white dwarf, you had some nucleosynthesis, okay? It didn't get very further out, so at the highest velocity material is still mostly oxygen, okay? But then as you go further in, you get some magnesium, silicon, calcium, and then near the center, you get mostly iron group elements. Okay, right? So you have a density, an abundance, a profile change with function of radius, but of course, as I said, it's better to think of that as a profile, the abundance as a function of velocity. Okay? And this is what you put into your radiative transfer code, and then you solve for it, right? So you have some power source. We heard about that from Brian. Okay, takes some time for the energy to get out, depending on the opacity, et cetera, and then you can build your radiative transfer model. Okay, so this is what it looks like. Here again, the red circle is the photosphere. Okay, so early on, optically thick, most of the energy is still being trapped or is going into expanding the star. Okay, so you don't see much, but then over time, okay, as the light starts to leak out, right, comes out, and again, you can see like absorption lines, they're all actually kind of p-signaling profiles, but it depends, how much emission, how much absorption you're getting. You get these different profiles. And then at late times, you can see it now, there is no photosphere anymore. There's no red circle anymore. You're seeing through the ejecta. And so now you just see emission lines. Essentially, there's no absorption. And it turns out, as we were talking about before, in this nebular phase, most of these emission lines are forbidden emission lines. The density is low enough that you get emission from forbidden iron, things like that. All right, so how am I doing in time? Okay, we're going to transition into actual supernovae. I mostly work on supernovae, not other transients, but I will show you some spectra of other transients as well. So I assume all of you have seen this kind of diagram before. We have this whole classification scheme. It used to be that spectra decided what a supernova was. Now it's a little bit more complicated, but generally speaking, it's still spectra. Do you see hydrogen or not? Do you see helium? Do you see silicon, et cetera? But it is a bit more complicated. Gru doesn't like it. Anyway, I don't know how we got to there, and it's getting worse. And many people in this room are adding to the getting it worse. So anyway, all right. This is a classic paper, Annual Reviews from 1997 by Alex Vilpenko, kind of a guru of supernova spectroscopy, showing you kind of what you see at different times. Okay, and remember one of the things, right? I said spectra tell you the chemical composition, but as Cecilia Payne taught us, right? So if you see a line, you know that that stuff is there and it's at the right temperature for that line to, make being strong. But if you don't see a line, does not tell you that material is not there, right? Because there, again, you might not be getting all the lines. Okay, so just by seeing the spectra doesn't tell you everything that you really want to know. But in a typical type 2, you see a lot of hydrogen. Okay, it's dominated by hydrogen. Okay, we have type 1A here, has these other things, no hydrogen, no helium in particular. 1B's helium, 1C's not really any helium. The difference between a 1A and a 1C can be a little tricky, actually, especially early times, things like that. But basically, this silicon line in the 1A is much stronger, and then at late times, they become quite a bit different as well. Okay, so here it is at late times in the nebular phase. We use brackets for forbidden lines, right? So all of these bracketed lines you see are nebular forbidden lines at these late times. Okay, you can see in the 1A, it's almost all forbidden line emission from iron group elements. Okay, whereas the core collapse objects, mostly they show a lot of oxygen emission, et cetera. Okay, at late time. So, late time is nice because you're optically thin, you're seeing through everything. That kind of gives you a better picture than just seeing like the outer layers or whatever that you see in the photospheric phase. All right, so that leads to this idea that we can split most supernovae into the thermonuclear ones, which are mostly 1As, and all the core collapse ones. And the difference between the core collapse is just how much of that outer hydrogen or outer layers of the star are still there when the star exploded. And so a type 2, you still have a lot of hydrogen left. Type 2b is sort of transitional, maybe you have a little hydrogen. Okay, type 1b, you still only have that helium layer on the outer part. Type 1c, you've stripped even the helium. Okay. And then also we sometimes have these broadline type 1Cs where it's this type 1C, but it's just everything is moving at a much higher velocity. That makes this photospheric velocity, it's the same line here, red and red, right? So you can see the P Cygni profile is quite different, much higher photospheric velocity. All the lines actually get broadened and blended together, and so you don't see them as well defined as you did in the normal 1C. Okay, so again, the spectrum tells you something about the speed of the ejecta. The typical widths of these lines tells you, how fast the stuff is moving. And then again, as Brian tells us, that's related to the kinetic energy, right? If you know the mass of the ejecta, 1/2 mass times this velocity squared is a measure of the kinetic energy. All right, so looking at core collapse 1, so we have this whole classification here, type 2 with hydrogen, type 2N, so that's N is for narrow lines. That is a sign of interaction. So in these narrow emission lines. Type 1Bs, strong helium features. 1Bs also have hydrogen most of the time, actually. It's just not very strong and you don't always see it. And so, there's 1Bs with a little bit of hydrogen. Even 1Cs can have a little bit of helium and a little bit of hydrogen if you get deep into the weeds here. Again, you can have, this is a relatively new class, 1BN, which is like a type 2, but it's a 1B, but then you have narrow helium lines. Okay, so these are interaction. What does interaction mean? Like the whole thing is explained, what is interaction? So the way I think about it, interaction is stuff that's not moving homologously, right? If it's moving homologously, we'll just call it the ejecta. That's the stuff moving out. Interaction means you're hitting something that was not, you're hitting something, right? Which doesn't happen in the race, like I was telling you, right? So someone is not moving fast enough. Someone was on the course, right? You're hitting that, okay? And then that leads to a shock. And usually what it means is like, look at these emission lines. Okay, does that mean we're in the nebular phase, late time, forbidden emission lines? No, these are usually permitted emission lines, Balmer lines, helium lines. Okay, so what's happening there? Shouldn't they be absorption lines? Remember back to our spectrum with the absorption line. When can you get an emission line spectrum? Well, when it's the stuff that's further out is hotter than the stuff in. And so when this material hits this other material that's moving too slow, you get a shock, it heats it up. And so that hot material is now on the outside. And so you just get these emission lines and the width of these emission lines tells you how fast that slower moving material was moving. That's why it's narrow. Okay. So you can learn again a lot about the interaction with these signatures. Yeah, question.
Sorry, again, not my area. So, but we heard a lot about nickel, but we don't see any nickel lines. Why?
It goes away. So, okay, we heard about nickel 56, it decays into cobalt and it decays to iron. So actually, if I go back, these iron lines in the 1A at late times, oops, right? Most of that actually came from radioactive nickel, or a good fraction of it. Okay. I'll show you later, I'll show you some JWST spectrum. We actually do see some nickel, which is at late times, but it's stable nickel. So nickel has many isotopes, but the two primary ones are nickel 56, which is this radioactive one that decays into iron. And so when you see the iron, that tells you that there was nickel. And the reason is actually just to nuclear physics, right? With a white dwarf, you start with carbon and oxygen. All the reactions that are happening, essentially all the reactions that are happening are strong nuclear reactions. So protons stay protons and neutrons stay neutrons. And so you started with carbon 6 and 6 and oxygen 8 and 8. They're only going to become like even things. And so you get nickel 56, which is 28 protons and 28 neutrons, right? And in that part of the chart of the nuclides, that's not the stable part. You need more neutrons than protons. So now that nickel has to wait, it has to inverse beta decay or electron capture. And then, so then you turn protons into neutrons, and then you go down one from nickel to cobalt, you get an extra neutron. You go from cobalt to iron, get an extra neutron, and then you're stable at iron 56, right? So that's what's happening. You need to wait for that weak nuclear reaction, which is slow, to get back to stability.
In a slider, so you keep showing a spectrum of a 1C and a 1C broad line,
yeah,
highlighting the same P Cygni profile.
Yeah.
If I didn't already know in that spectrum
Yeah.
that it was a 1C broad line,
Yeah.
and I'm just trying to identify something, how do I tell the difference between a P Cygni profile that is that blobbed out
Yeah.
versus just like a very high velocity emission line?
Of something else, or yeah, it's not easy, right? So, one thing is, once you have a spectrum, it's pretty easy to take it and say, what if I had a higher velocity version of it? What would it look like if I had a lower velocity? So someone did that and said, hey, actually, all these peaks line up if I just crank up the velocity, right? And so, yeah. Eventually it becomes so blended out that you don't know what you're looking at anymore. It's yeah. I'll show you some more examples of that in a second. Okay.
Can I ask a question
Yeah.
about the slide?
Yeah.
So this goes back to what you started off with, one of the first slides. Why would I necessarily have the circumstellar material at a higher temperature rather than these, I don't know what the terminology is, but the equivalent of, this line being photoionized or photoexcited.
I'll show you that in a second too. So you can have all of these things. Generally what's happening is there's a lot more energy in kinetic energy than thermal energy, right? And so what happens is when that material crashes into this circumstellar material that was just minding its own business, right? It gets heated up to very high temperatures, actually usually like X-ray temperatures compared to like the optical UV temperatures that we're talking about. So it gets very hot very quickly, right? Because it's thermal energy, kinetic energy that is hitting and you get a shock, and that's, that radiates.
But then the post-shock material is also moving at a high velocity, and these lines will be shifted and broadened because it's
So if you watch these, there are other people in this room who are more experts at 1BNs. I don't know if you watched how these emission lines change. They do change with time, and yes, you would expect that shock to move inward and outward. So you get actually this double shock structure, and it will change the profiles of what's going on. Yeah. They cool pretty quickly, is my understanding too, because they get heated to these huge high temperatures. There's X-rays, radio that comes out, and then they cool. And
so my question is, I guess I didn't understand whether the narrow emission lines come from the upstream or from the downstream.
Like, my understanding is they can come from both shock gas that has been accelerated by the shock and by gas that's upstream that has just been irradiated by, UV or X-ray and is heated. So the local heating by the shock and also photoionization heating. I think both can happen depending on the event, but I could. I'm happy to be corrected.
This is why I work on 1As that don't have interaction, so I don't know the answer.
No, but you see high velocity ejecta, narrow unshocked material, and you also see intermediate velocity shocked, decelerated ejecta. So you see all three.
Is someone talking about circumstellar interaction more here? I just don't know the answer to your question. It is a great question. I don't know the answer.
I think Anna might talk about it when talking about efforts.
Okay.
But yeah, so if you look more closely at the lines of these things, what you see is that you can never explain the line profiles with a simple Gaussian that you would expect from a single velocity. It's always a superposition of a broad Gaussian, which is represents the broad base of the line, and then a narrow Gaussian that lives on top of that. The idea is that the broad Gaussian is closer to the expanding ejecta. It's traveling at 1,000 kilometers per second, and the superimposed narrow component comes from this photoionized gas that has not where the ejecta hasn't reached that gas yet, but it's sort of shining that gas with X-rays, and that's what photoionizing it, and it's recombining to produce those lines.
But so then that doesn't tell me anything about the temperature of the upstream, because it's photoionized. It's not in thermal. It's not in it's not collisionally ionized. It doesn't tell me anything about the temperature of the upstream.
Right. I mean, the upstream material is presumably something that was left behind from the progenitor stuff.
But I think that's good actually, because it tells you that helium, it's not just because the temperature was not hot enough in a 2N to not, it's basically like saying that in this 1BN, there wasn't hydrogen also there, right? It tells you like it was helium rich material that was the CSM.
It couldn't be there and just be fully ionized.
I think you would still get the recombinations that make all those lines, right? Like that is the recombination cascade of, going from 3 to 2 or 4 to 2 or whatever. See, I'm an observer, so you should talk to the right people. Okay, let's keep going. Okay, so type 2s. So here, we saw that beautiful type 2 light curves from, again, for Brian here, kind of a cartoon version of what that looks like. They stay at constant luminosity as this recombination front goes through this massive hydrogen envelope. And so what you can see is during that time, which, maybe 100 days, that here's an example, that spectrum also doesn't really change much. Okay, but what you do see, and this was, we were talking about this earlier, if you look at these P Cygni profiles for the H alpha, notice that they are getting narrower over time. And so you're literally seeing that photosphere recede into lower velocity material as you watch that. And then eventually it gets through, and then you see something else, okay, and before you see that stuff at the outer parts. So you really, people talk about a CAT scan or of the supernova. That's kind of what you get with these time series of spectra. Okay, interesting in the UV. So type 2 supernova in the shock breakout, it gets quite hot. It puts out a lot of UV emission, but there's so many lines in the UV, especially for iron group elements. If you have a bunch of iron and a lot of UV light, those photons do not get out. And this is what we see in 1As. We don't see very much UV emission. Sometimes for type 2s, though, there isn't that much, and so you can get some UV light out, but it can change a lot. And then, so this says there wasn't much iron group elements in the outer part, so you got a lot of UV out earlier on, but later on, okay, even though the temperature is probably still hot enough to get some UV, you can see this strong suppression, and that's probably because there was more iron-rich material closer, at lower velocities.
Oh, so the iron is just deep in the ejecta.
That is one interpretation of this. Yeah, you have to look at the modeling just to make sure it's hot enough also to excite it, but that's why you see the UV early, but not so UV phase to the optical. Yeah, that is at least what this paper is arguing. Okay, one thing which is relatively, maybe this is a decade and a half ago. It's hard when you get old, time compresses. So I don't know how long ago people discovered these flash spectra, but here's a really nice compilation of. By the way, the references I have, it was just like either a paper that I'm on and I remember the figure, or some other recent paper. It is not meant to be like, oh, I found the best reference for all of these things. So just take it as a typical example. There are many papers on all of these topics. But what you see here, this is what's called flash spectroscopy. So when that shock breakout happens for a core collapse object, and like a type 2 especially, it photoionizes the surrounding gas. And so you can see, again, emission lines from recombination of many species. In fact, like some relatively hard to ionize species, you get strong enough photoionization to get like nitrogen-4, things like that. Okay. And this only lasts for a few days. The recombination time is generally hours to days. And so you have to get on the supernovae early. And I guess we're going to hear about how you discover these transients with Ruben. And like my whole talk is something Ruben is not going to do, spectroscopy, right? And so, people will have to be able to get the spectra quickly to study these things. And, there are many surveys nowadays, including CCA, for example, which finds objects early enough that you can see these flash features, which flash for a couple days for a bunch of objects. Okay, but it's really nice because you've shown this bright X-ray UV light on the material ahead, and as you can see what was there before the ejecta run into it. So you can learn a lot about the progenitor star by trying to study this flash spectroscopy. Okay, UV is interesting. Like it's quite a huge variety in type 1 supernovae. Some quite UV bright. So this is a superluminous supernova, has a lot of UV. So that would imply not so much iron there. But again, no one knows what these are. But then for like a 1A or some other types of type 1 supernovae, pretty UV dim relative to the optical. These are all normalized at optical wavelengths. And you can see orders of magnitude difference in the UV. Okay, one cool thing, this is a little movie that my former grad student, Lindsay Kwok, who's now at Northwestern, made. So we're looking at late time, so nebular phase, where it's completely optically thin, so you get to see through the ejecta. And again, here's another visualization of like how the wavelength tells you these different slices through the ejecta. Okay, so again, you're basically taking these slices, and that's going to tell you the emission line profile through the ejecta. And if you imagine it's completely uniform emission, uniform emissivity throughout this whole sphere, you would expect this particular line profile, which actually you can calculate it. It's a simple integral. It's just a parabola. It's just a quadratic function centered at 0 and then to the two extremes in the velocity. Okay? So this is the kind of line profile you'd expect to see at late times for uniformly emitting, constant density, constant emissivity, spherical ejecta. But you can play around with this. It's actually, it's just the same integral. You just have to, you can change the geometry however you want. You can change the emission properties as a function of velocity however you want. Calculate the line profile. At late times, it becomes fun and easy to do. So you can do something like this. You get a flat top profile if you have a shell of emission, right? You're missing the emission from the center, so that cuts off the peak. And so you get this kind of flat top. You can have a little asymmetry. You can move this shell off center, and then you get kind of this profile that goes like that. And the reason I'm showing you this is actually in data that we have taken with JWST of late time spectra of type 1As. And I guess I'm talking again about 1As in a week. I haven't written the talk yet, so this might show up again. But actually you see, so here's, this is a nickel line. So someone was asking about where's the nickel. This is a nickel line, this round one. Okay, so this is nickel 58. This is stable nickel a few hundred days after the explosion, but it is there near the center, right? It has that nice spherical distribution profile. But here is an intermediate mass element, so-called argon, which has this tilted flat top structure. Okay, and so you can see the line profiles for these two different elements are quite different. So this is argon, here's calcium, two intermediate mass elements. They have these kind of sloped flat top profiles. And what that's saying is that the nickel is interior in a kind of spherical distribution, and the argon and the calcium are in a shell around and a slightly off-center shell like this. And the fact that one of them you see tilted upwards and the other one you see tilted downwards can be explained by the viewing angle relative to where this offset is, right? So this is why we're so excited by JWST, because things become optically thin in the infrared much easier. I'll show you that in a second. But also at late times, you can study like through the ejecta, you can kind of learn a lot about, right? So this is telling you something about the structure of the explosion. We think it has to be a detonation to make this layered structure. Yeah.
So basically we would get some kind of like a flat top, profile from off-center like shell, but what if it's like a blob or like some kind of like other geometry?
Yep. So it's basically just take that movie and just put your blob wherever you want it, slice through it, and if it's all emitting the same way, that's what you would see. So you would see if it was just off-center, you would see a kind of a Gaussian type profile, but just shifted, in velocity. Okay. So one thing here is that this structure doesn't tell you that there's no argon there. It tells you there's no argon-3 emitting at that line. So there could be some other reason. Maybe all the argon near the center is ionized more than this, or ionized less than this, and so there's just not any argon-3 there. Or maybe that level is not populated. So you have to, again, be a bit more careful and do an actual model to say, oh, the reason it's not there is because there is just no argon there versus some other reason. But indeed, you could have blobs, you can make it more complicated. Now, there is some spherical symmetry built into this whole, slicing through assumption. But yeah, if you can make your model in that space, you can just construct, what is the emission at every point, and then that should lead to the line profile at late times. All right, turns out there's a lot more in the white dwarf supernovae than just 1As. That may be news to some of you, but I'll talk a lot more about this in my 1A talk next week. But one kind of cool thing is that they kind of all look the same in the optical, but they look quite different in the near infrared. And so you could see these different, this is what we call the thermonuclear supernova zoo, where normal 1As are here, but there are these other examples of weirdo 1As or extreme or peculiar 1As, and they have quite different spectral signatures. Ones that I really like, which I worked on for a lot of my career, are these type 1AX. They are very low velocity versions, right? You saw the 1C broadlines, very high velocity version of 1C. Here's a very low velocity version of a 1A. Low velocity is great because you get to see all the individual lines. They're less blended. So I like low velocity stuff. High velocity stuff is just harder to interpret, just like we were talking about. So I really like all this low velocity. And so in fact, the title slide was type 1AX supernova. If you knew me, you could have guessed that. But those were type 1AX spectra. And one really cool thing about this is relatively early time. And so in the optical and UV, it's all photospheric. They're P Cygni profiles. There's a lot of absorption. But watch what happens as you go to the infrared, especially the mid-infrared. Notice all the line profiles have changed to become basically emission lines, right? And we're talking about, just like in this room, the optical depth is a strong function of frequency. Well, here it's the opposite way. This is optically thick in the optical, but very optically thin in the mid-infrared. And so there is no photosphere in the mid-infrared. And we actually, even at a few weeks after the explosion, we're seeing through all the ejecta at that time. So what's nice is in one epoch, one panchromatic spectrum, as Lindsay likes to call it, you get the optically thick part, and then an optically thin part, and you can kind of learn about what's going on in different places all at once. Okay? And then again, these are very low velocities. All of this, none of this is noise. These are all lines at very low velocity. Okay, the other end of the spectrum here is type 1Cs. Here, the broad line I mentioned. So here's a paper by Mario Mojaz comparing the normal type 1Cs and the broad line ones. And it's a little hard to see in this figure, but look, concentrate on the black curve, right? So here are the line features, and then here they are in the broad line, right? It's all high velocity, so it also loses contrast, right? The heights of the peaks get kind of washed out, right? So it's harder to see those, right? So the question was, how did you know, or how did anyone know that this was just this? Well, it was like taking this, smoothing it out with a, just put a Gaussian velocity kernel on it, smooth it, you get something that looks like this, and you say, I think it's the same. This paper actually also looked at whether the 1C broad lines, so by the way, every GRB, gamma ray burst, that had a supernova associated with, if someone took a spectrum, the spectrum was a 1C broad line, okay? But there are some 1C broad lines that did not have GRBs. And as far as this paper could tell, there was no easy difference you can see in the spectrum that could tell you whether this had a supernova, had a GRB or not. Okay, so all GRB supernovae are 1C broad lines, but not all 1C broad lines are GRBs, and people don't know what makes the difference. All right, let me talk about 1Bs, because 1Bs are kind of like the neglected middle child. You have 1As and 1Cs. So this is for Kishalay. So there's an interesting group of 1Bs, which are called these calcium-rich 1Bs. And so you can ask him about it. But what's interesting is most core collapse supernovae, they produce a lot of oxygen. And massive stars have a lot of oxygen, so there's just a lot of oxygen. In fact, the oxygen you're breathing right now almost surely was from a massive star that got to you eventually because of a core collapse supernova. But these calcium-rich ones don't have very much oxygen, and so we don't know why that is. Oh, sorry, I just have a thing in there. I'll get rid of that. There's a still open question whether these are truly core collapse supernovae, which Kishalay's papers argue, or there are other people who argue that these could be thermonuclear supernovae. They happen in they're 1Bs, which would say that there should be core collapse. They also happen in these weird environments, and so it's hard to figure where there isn't much evidence of star formation. So it seems hard to explain. But they have these very, very strong calcium things. Okay, I'm getting close to the end. That was actually almost all the slides I had, but then Brian had his talk with all the different, from Monty's diagram of all the different, I said, I should probably have spectra of every class that was on there. So that's what I was doing during Brian's talk, is getting spectra of all the different classes. Superluminous, there's type 1 superluminous, if like GRU would be losing its mind at this point. Type 1 superluminous, type 2 hydrogen rich, hydrogen 4. The hydrogen 4 ones are really cool. These hydrogens everywhere, so those are less cool. That's my personal opinion. But anyway, superluminous supernovae, very strange. We don't know what they are. Tidal disruption events. So again, we think we know what they are. These are stars that get too close to black holes and get disrupted. So again, they have fairly unique spectral signatures. Again, I don't know that all of these have been explained in exactly what's going on. We heard about this extended photospheric phase Brian mentioned and stuff. And so, yeah, unclear exactly what the spectra are showing, but there they are. They do look like each other, at least. That's good. These intermediate luminosity transients, have relatively narrow lines. So it's, whatever's happening is a kind of low energy kind of thing. But anyway, they also share some similarities. Luminous red novae are not actually that red. They're red at late time, so they become red, but when the nova goes off, it's actually fairly blue, as what you see here. But later on, they become these very red things. So again, spectra are telling you here, these are generally molecular. When you see these broad lines, you might be like, oh, there's something moving at really high velocity. Generally, no, this is pressure broadening of molecules. So in fact, if you took a spectrum of the Earth, you would also see broad lines. And it's because of pressure broadening. What is pressure broadening? It's the electric field of neighboring, density is high enough that the electric field of neighboring molecules change the levels of your other molecule. And so that smears them out. Nothing is actually moving very fast. Okay, so it's like you got to take your neighbors into account when you solve the Schrodinger's equation. All right, I think, oh yeah, we have 1 kilonova spectrum, maybe more, but basically, so then this also looks interesting. There's a rich literature out there about whether from these spectra, so Brian talked about what is the power source for a kilonova. We think that our process, nuclear synthesis, is really exciting. And if merging neutron stars make all those heavy elements like the gold or platinum maybe on your jewelry. It'd be great to see some spectral signature of that. And I would say the jury is still out. Some people have claimed that they see like R process type lines. Basically, this, if there's not that much iron, this kind of very red color suggests that there is something with a lot of line opacity at these wavelengths. And in fact, it extends further into the optical than it would for iron, which is mostly just in the UV. So that is indirect evidence that many of these like lanthanides and actinides with lots of lines in these regions were made. But direct evidence, like, I want to see that platinum absorption line, which still waiting for that. Okay, in the last 2 minutes, so how do people model these? I'm not a spectral modeler. I do work with the TARDIS collaboration a bit. There are many models. There's sophisticated ones, 3D radiative transfer codes. Usually there's a separation. The people who blow up stars or make transients, and then they feed their outputs to a radiative transfer code that does it. Could be 3D, could be complicated. TARDIS is a 1D version. It makes a lot of assumptions, but the nice thing about 1D is you can get plots like this, which show you like, what was the last thing the photon did before it got to you? It got absorbed by this particular element. So you can kind of make little things like that. And then with the right inputs, TARDIS has done a good job of being able to model many different kinds of supernovae. So that's nice, from core collapse to thermonuclear, 1As, type 2s, et cetera. Okay, here's just one example of that. So this, of course, my favorite 1AX. This is from my former PhD student, Isa Camacho Neves. We collected 500 days of spectra of this type 1AX. One of the interesting things about 1AX is they don't become fully nebular. They don't become optically thin totally. We think that's because the white dwarf did not completely disrupt, and there's something still left behind, a compact remnant at the center. So there's still an optically thick photosphere at late times. And so you can use TARDIS to model it. And so you collect a whole bunch of data, and then over 500 days, which is hard to do, but the same TARDIS model, the same explosion model, fits the data over this very long period of time. So that's really nice. The same radiative transfer code applied to the same underlying explosion. And so we do think these are these partial explosions of white dwarfs that did not completely unwind. All right, last slide here. Why is any of this of interest? We talked about this about the oxygen, but basically everything, most of the elements that we care about, the iron in your blood, calcium in your bones, et cetera, all came from either massive star explosions or my favorite, thermonuclear superstar. The thermonuclear ones are the 1%, the best, right? We all know that the 1% are the best, right? So the 1% of you and me are from thermonuclear supernovae, the rest from these massive star explosions. But yeah, so spectroscopy is the key to understanding that. And so that's why, we want to keep getting spectra and understanding them, even in this era of Rubin. Spectroscopy will be very important to understand all these astrophysical transients that Rubin will provide. All right, thank you.
I have a rather provocative question when it comes to the kilonova spectra, because I agree with you that we didn't see, we don't have a definitive line identification, but I think there's another way. I think there are some lines people have claimed, like a strontium line, and I guess if we saw, so if you see a line in a supernova that you can't identify, is that itself proof of, say, exotic material, or would you say that our line list is incomplete? So we don't know for ordinary elements, we have sufficiently complete line lists now that there should be no mysterium. Yeah, anyways, this is, yeah.
Yeah, so in fact, in our JWST spectra, we have many of these. And there it's even easier, like, roughly what levels could be populated, and you roughly know what ionization. And so we still see some things which are, they're all relatively low-lying levels. You think someone did the calculation, but no, in fact, recently, even calcium 4 or whatever, the line lists, someone did the calculation and experiments, and they're increasing the atomic data. So the atomic data is not really there, even for things which we like. You have to really show it's not iron or everything else that you know about before you go to strontium, and that's hard.
So separate from the question of deciding which of the millions of transients to follow up with spectra, what is, like instrumentation wise, what instruments are the best spectroscopic complements to LSST?
Yeah, so that's a great question. I don't know the right answer. One of the things that you can see is like one thing I didn't really talk about is spectroscopic resolution, right? So what do you need? And so, for example, with ZTF, there's a instrument called the SED machine, which gives you resolution of 100, R of 100. And so if you just do R of 100 means delta lambda over or lambda over delta lambda of 100. And so that means you can think of that as V over C is 0.01. So it basically means it can resolve features at around 3,000 kilometers a second. And that's pretty good for most supernovae. Okay, it turns out for like 1AXs where like this features could be like 2,000 or it becomes hard, and suddenly all your 1AXs start looking at like 1As, right? Because you're just observing them at low resolution. The nice thing about low resolution though is you're not taking the light and spreading it out as much, and so you can go deeper for that. So there's all these trade-offs, and someone asked like, oh, what's the best camera to have? It's like the one you have on you. I think like what's the best spectrograph to have is the one that can observe right now from your Rubin transient. And so if it has it's infrared or UV or optical, whatever resolution, like there's a minimum. I think R of 100 is kind of close to that minimum. But yeah, I think it's going to be all hands on deck, because like people are going to have to. The one thing about Rubin is like there'll be a lot of objects that exploded yesterday, and you'll hopefully know about them, and you can then decide, okay, I have this particular spectrograph. This is the most interesting science target for me. And we might be still in the mode where that one spectrum is a paper, right? And so if you think about like what are the outputs here, like yeah, hundreds of thousands of transients, but the one that you got the spectrum of because it was like 6 hours from explosion, and you had the right instrument to do some interesting science about a flash spectrum or whatever it is, I think that's where the science is, right? And so the idea is to figure out what capabilities you have, apply it to the right thing, and get good science.
But just to sort of bring that back, I think the reason we are having this school in the first place is because there are just not enough telescopes on the planet to follow up everything from it. It's impossible. So, which is why we need to be smart about the kinds of things we want to follow up, especially leveraging what the kinds of transients that LSST will be good at. And that's so. In case you were flabbergasted about all this light curve talk and spectra talk today with all the diversity, kind of the motivation for doing it on the first day is because for the rest of the school, we'll be going into each of these individual classes separately and talk about sort of what their characteristics are and what the questions we are interested in. Questions? Right, let's thank Saurabh again.